So welcome everybody. We're going to go ahead and get started for the Polar Climate Working Group winter meeting. If you don't know me online or anyone else, I'm Alice Duvidia. I'm one of the co-chairs, and Hansi Singh is the other co-chair. She is online, and if you're there, Hansi, can you unmute and say hi?
Hello. Can y'all hear me?
Yeah. Yes, we can hear you.
Great to
Good
see
to see you.
everyone, or kind of indirectly seeing everyone filing in.
Okay. So Hansi and I are going to be together kind of running this and running the discussion today. But before we get started, just a couple things. So just in terms of meeting rules, the main thing is just be kind, treat everyone here like you would want to be treated with questions and stuff like that. Give everyone a chance to engage. So share the air, let everyone speak, appreciate people, listen, communicate, all of that stuff. Basically be a good human. The logistics and rules, the first one they've told us many times, and I think you can probably tell from this barrier, don't touch the screen. So if you need to, there is this pointer. There is a pointer, it's a virtual pointer, and now I don't know how it's working. Oh, there's some sort of virtual pointer, or you could use the mouse if you need to for pointing stuff out, but they really don't want to touch the screen. The meeting is going to be recorded. It'll be available under some sort of password protected thing after this, so it's not being aired to everyone right now. If you are here and you're a visitor, there's a UCAR visitor wireless that you can join if you don't have EduRoam. And then today, the general schedule is we'll have about an hour of talks, we'll have a break, we'll have some more talks, and then we'll have our first discussion. And you should be able to find the agenda, the full agenda online. I didn't put it all here. And then the final thing, I have been told that this map is maybe a little confusing. That's okay. If you came in from the driveway here, you went up some stairs and through the front desk, and then you went up some more stairs and we're here in the main seminar room. And if you go down those stairs again, there's a men's restroom and water down here, and then just around the corner, there's a women's restroom. Not relevant today because most people have already eaten, but if you go kind of around the corner here, there'll be a cafeteria tomorrow. And then on the second floor, if you need other bathrooms, we're kind of in this weird like 1.5 level. We're not really on the first floor or the second floor. So if you go up the stairs as you come out of here, if you turn left, there's an accessible all gender restroom. And then if you go right, there's a men's restroom. And then if you go a little bit farther and then turn a corner, there's a women's restroom. And if you need power, it's under the seats in here. So I think that that's everything. So without further ado, I'm going to invite our first speaker. Oh, and for question and answer, if you're online and you have a question, you can put it in the chat or raise your hand and we can light you up during your question time, or I can read it out to the room if you would rather. And if you're in the room, they're going to turn on the overhead mics so that you can just ask your question and people online should be able to hear. All right. Yeah, next it should go through.
Okay.
All right, so our first speaker is Ash Gilbert from CU Boulder.
Hi. So today I'm going to talk about isolating the contribution of observed winds to recent Arctic warming and sea ice loss. I'd like to thank all my co-authors and say that this work was funded by a National NSF Graduate Research Fellowship and Arctic Natural Sciences Grant. This is my candidacy work, shortened, and I'm hoping to submit it to Journal of Climate by the end of April. So as you all know, the Arctic is warming quite faster and much faster than the rest of the globe, but so this exact magnitude remains uncertain. So for example, here's the CESM1 large ensemble with the Arctic and global rates of warming, and you can see there's quite a lot of spread between all of the members. Similarly, there's quite a lot of spread in the Arctic amplification factor. But we do know that the ensemble captures the observations, but despite knowing that, we have a lot of internal variability, which sort of adds this unreducible uncertainty into our sort of projections of Arctic climate. So we do need to understand the internal variability of the Arctic climate system better. But from previous analyses like Ding's fingerprinting study, we do know that the observed winds are critical to reproducing the observed sea ice and temperature trends in internal variability. So what if we could prescribe that perfect observed circulation that gets us that reproduced internal variability pattern? We can with wind nudging, where we nudge model winds to observed winds to reproduce sort of the observed circulation in the climate model. And two examples that are the Ding 2017 study where they did nudging in CESM1 and were able to sort of reproduce the pattern and trends of sea ice loss in September. And the Roach and Blanchard study, Blanchard-Wigglesworth study in 2022 that also did temperature, looked at temperature and sea ice with nudging. Their nudging is in the red. And they were able to reproduce the observed interannual variability and trends much better than just the large ensemble by itself. And so, yeah, like I said, these studies were able to show that the observed circulation is able to replicate Arctic warming and sea ice loss and variability. Sorry, I'm having to talk very fast to get through this. But given the design of these nudging experiments, both Ding and Roach were able to ask, how much did the observed winds contribute to sea ice loss? Ding found it was about 60% from summertime circulation, and Roach and Blanchard was about 20 to 25% from the observed circulation total. But all of these previous studies from Ding and Roach evaluated the combined effect of anthropogenic forcing and the observed circulation to get this assessment of wind contribution to observed trends. But what we don't know is the exact influence of the observed winds on Arctic trends in the absence of anthropogenic forcing. So that's what my study aims to do. So we're looking at the influence of observed winds alone on the Arctic warming and sea ice loss trends and interannual variability, the seasonal temperature and sea ice extent, I should say extent trends, sorry, and the local trends in temperature and sea ice. And an additional factor we looked at, since the influence of the winds is dependent on mean state sea ice thickness, because thicker sea ice is responsive or less responsive to winds and warming, we added this question: how do these results change for an increase in mean state sea ice thickness? So here's the just the brief setup of the model configuration. I'm using CESM1 2.2 or 2.1, sorry. And I used a pre-industrial climate because, again, we do not want the anthropogenic forcing. And for nudging, I nudged the horizontal UNV components with ERA5 data every 6 hours between 1950 and 2023, over 60 to 90 north and above 850 kilopascals. We're only looking at the synoptic scale wind. And so here's all the data sets that I ended up using. For OBS, I used ERA5 and GISTEMP. And then it's sort of a baseline for our pre-industrial climate. I took 51 74-year-long slices from the CSM2 pre-industrial control to sort of get a measure of the internal variability of the pre-industrial climate system. PI nudge is sort of the default pre-industrial ensemble. It's been nudged with ERA5 winds, and then PI nudge less melt is the same as PI nudge, but it's got those thicker sea ice modifications from K et al. 2022, the less modifications. Yeah, and these are just sort of like, why we have each experiment. Yeah, again, CSM2PI is our baseline. So sort of the benchmark for performance. All right. Also, I want to say that we did have to diagnose and remove wind nudge-induced model drift. If anyone wants to learn more about that, I have plenty of plots, and I'd be happy to chat about it afterwards, but for sake of time, we're going to have to skip. Yeah, so jumping right in, Arctic temperature trends and variability. So here's the annual Arctic temperature from 1980 to 2023, and for all the results, that's sort of the time frame we focus on. And for the rest of the line plots, OBS will be in black, the bounds of CSM2PI are going to be in light blue, PI nudge will be in dark red, and the PI nudge less melt will be in teal. And let's say the closer to the OBS, PI nudge and PI nudge less melt are, the stronger the wind influence, and the closer to the CSM2PI, these two are, the smaller the wind influence. And if the PI nudge and PI nudge less melt are sort of within the CSM2PI bounds, they're basically within what we'd expect for an internally driven climate. And as you can see, all right, as you can see here, neither wind nudge experiment reproduces the magnitude of the observed trends, and both experiments end up reproducing about 20% of the interannual variability. And for detrended anomalies, which is sort of the second value on the right, PI nudge explains 24% and PI nudge less melt 16%. And again, as expected, PI nudge less melt has a colder mean state climate than PI Nudge due to those sea ice modifications, and PI Nudge is mostly within the CSM2 PI envelope, so the winds are not really having an effect on the mean state temperature. Now looking at the monthly and annual trends for the Arctic temperature. Again, neither wind nudge experiment reproduces the magnitude of the monthly or annual trends. For example, if you look at the annual trends, observed is 0.71 Kelvin per decade, and PI Nudge and PI Nudge less melt are about 0.12, 0.112 Kelvin per decade, which is not very much. They do reproduce roughly the seasonal pattern of trends, and both experiments are within values we would expect for a pre-industrial control. But one interesting to note, both PI Nudge and PI Nudge less melt have very similar trends, so the thicker sea ice isn't really having an effect on the warming trends. So in summary, the winds alone cannot reproduce the observed annual and monthly warming. They can explain about 24% of the inter-annual variability and the seasonal patterns of warming, and that the warming is independent of mean state sea ice thickness. Okay, onto the sea ice, extent trends. This is the September sea ice extent. Again, you can see neither wind nudge experiment is reproducing the observed trend, and both experiments explain about 11% of the interannual variability, and PI Nudge less melt has slightly more sea ice extent because of those sea ice modifications. And again, PI Nudge is mostly within that envelope of pre-industrial conditions, so they're not having, the winds aren't really having an effect on the mean state September sea ice. Going to March, again, neither wind nudge experiment is reproducing the observed trend, and both experiments explain about 1% of the interannual variability. And again, as expected, PI Nudge less melt has slightly larger mean state sea ice area. And both experiments this time are within the CSM2 PI, but they have this interdecadal oscillation that is not present in the observations. But when we look at AMOC, and we look at the AMOC transport, we find that this March sea ice oscillation that we have is reflected in reverse of the in the AMOC circulation. We think that because of this, the oscillations are likely connected, but this is sort of beyond the scope of my study and definitely merits further research. And so here's the monthly sea ice extent and annual trends. Again, neither wind nudge experiment is reproducing the monthly or annual trends. Yeah, for September, the odds is 0.92 million Kelvin squared per decade. The wind nudged ones are much smaller. Same thing for March. But both experiments do roughly reproduce the seasonal pattern of sea ice loss trends, and they're both within values we would expect for the pre-industrial control. And again, PI Nudge and PI Nudge less melt have very similar trends, so these thicker sea ice is not having an effect on the sea ice loss trends. So in short, the winds alone cannot reproduce the observed September, March, and monthly sea ice loss. They can explain about 12 to 1% of the interannual variability and the seasonal patterns, and sea ice loss is independent of mean state sea ice thickness. Okay, I think for the sake of time, I'm going to skip the local trends. The long and short of that is that the winds alone cannot reproduce the magnitude of local and warming sea ice loss. They can drive the regional patterns of warming and to a lesser extent sea ice loss. And the local warming and sea ice loss are independent of mean state sea ice thickness. So this is what I'm currently working on. So I'm going to add a PI Nudge more melt experiment to sort of form a more complete understanding of how the observed wind circulation depends on the mean state sea ice thickness. And I'm trying to spin up a more melt pre-industrial control and investigating different combinations of SICE nameless changes. So I've tried 4. The top 2 have not worked out. The other 2 I'm in the process of testing. And like I said, these are the combinations I've tried. I'd love to hear if anyone else has any other ideas. Yeah, and so the results from those. So This is the monthly sea ice volume in the Arctic. As you can see, I compared it to the less melt in blue and the sort of the baseline pre-industrial control in black. And as you can see, the red baseline more melt control and the more melt DT melt, those are closer to the baseline CMIP control than I'd like. The other two, the more melt PSI and the more melt R snow 0 have much less sea ice, but I only have 50 years of those. Well, I should say only 50 years. There are 50 more years sitting in my archive. I haven't processed them yet. That is to do sometime this week. And then this is the annual sea ice volume. You can see that I stopped doing the more melt because that converged back to the baseline. But the other two, the R snow and the PSI, those look much better. Yeah, I'm hoping to add these to my paper before I submit it in April, but I may run out of time. Yeah. Yeah, so in short, the observed winds fail to reproduce the magnitude of recent Arctic warming and sea ice loss, and they partially reproduce the interannual, seasonal, and spatial variability of Arctic temperature and sea ice loss. And basically, in short, the observed winds drive Arctic variability, but not long-term trends, and our results are independent of the mean state sea ice thickness.
All right, thank you, Ash. Are there any questions in the room or online? Okay, I think the roof mics are on. Okay, go ahead and ask. Yeah, they took mine off.
I'm curious if you've tried to do anomaly wind nudging so that you keep the pre-industrial climatology of the winds, if in case they should be different than the observed present wind climatology.
I've not tried to do anomalies, but I did do an analysis of the observed winds and compared them to the pre-industrial control. So for example, this is the zonal 350 kilopascal level winds trends. And any stippling would be basically outside of that pre-industrial control that I tested. And basically for both U and V, there's like nothing outside. So
They look good.
yeah.
That's great.
Anyone else in the room or online?
Hi, this is Alec.
Okay, go ahead, Alec.
Yeah, I was just wondering, I maybe missed this, of what's causing the little extra summertime trend due to winds? Is that a loss export term, do you know, or a heat advection source or something?
In the sea ice or temperature?
In the sea ice loss,
Okay.
you have like a little summertime increase due to observed winds. Just wondering what.
This one?
Maybe, yeah.
Yeah, we just haven't really thought about that much, but my guess would be that just the winds during that time of year are, at least the observed winds, are more conducive to sea ice growth. And in this pre-industrial climate, they actually create sea ice growth, and instead of a historical climate where they sort of have the background forcing, and you just see like a net loss.
Mm-hmm. Interesting. Cool. Thanks.
All right, so I think to keep on time, we're going to go ahead and thank Ash again. Our next speaker will be online. Claire, are you there, and can you share your own screen?
Yes. Give me a second. Okay. Does that look good?
That looks great. So this is Claire Moody, and she is a student at University of Wisconsin-Madison. All right, go ahead, Claire.
Awesome. Yeah, thanks for the introduction. So for my PhD work, I'm looking at the role of intense summer cyclones in the Arctic, and specifically how they impact the marginal ice zone. So what I'll be talking about today is looking into the CSM2 large ensemble. But to start, I thought I would just quickly present a quick little case study using observations and reanalysis, which we can see up here, developing with this nice spiral-shaped cloud. So just to begin, we're going to flip around and orient ourselves that way north is up. And so then for each cyclone, what we've done is defined a storm impact area based on the 1,000 millibar contours of each day of the cyclone, and then isolated the marginal ice zone, which in this case we've defined as all points that are within 15 and 80% TA concentration over the 3 days of the storm. And we're going to track how that area evolves. So looking first just at the first day change, we have the near surface winds plotted on top, which has a very typical cyclone structure where we have these weak northerlies to the west and strong southerlies on the east, which are corresponding and right on top of this very large decrease in sea ice area. And so what we're going to do next is track these changes from 1 week before the start of the storm through 2 weeks after. And so up top, we have this change in the marginal ice zone area. The dashed line is the 10-year decadal climatological mean. And so sort of what we would expect to see if there wasn't a cyclone here, just a steady decline. And we can see in the solid line, which is our 2017 time series, that prior to the storm, we're right along that sort of seasonal melt. And then right as the storm starts to develop, we see this large departure from that mean and this large decrease in ice area that then continues for 2 weeks on after the storm. And so two of the main characteristics that we looked at from the storm are the winds. And we see that during the storm, we have most of the marginal ice zone being affected by these really strong southerly winds. And then throughout the storm, we also see these increasing SSTs, which then continue to increase through well after the storm. And so this is just one example case. But if we then expand this to a large census of storms, where we'll first take this time series, subtract out the sort of seasonal change, and then normalize by the area of the storm impact region, just so we can find sort of this average impact of any given cyclone, regardless of its size. We get these really kind of variable plots. So we looked at 2 different decades, the 2010s and the 1980s, and then separated it by early summer storms, June and July, and late summer storms, August and September. And there's just a ton of variability here. We can see that, in this case, we have one really strong ice enhancing storm, but one storm that causes a large decrease in ice area. But then these sort of mean trends and tendencies do emerge once we kind of get an average sense of what's going on. And so we see that in the early summer months, there is this kind of steady decline, right? Particularly around the days of the storm. We see that the July months are maybe a bit more, tend to decrease area more than the June storms on average. And then if we look at the late summer storms, they have very small, little to no net effect. And we see that the positive impact of the September storms tends to kind of balance out this negative impact from the August storms. And then comparing the 2 decades, we also see, just looking at this normalized change, that there are much greater impacts more recently than the smaller envelope of impacts in the 80s. And so now what I'm going to talk about is seeing how these trends are represented in the CSM2 large ensemble, and if there's a fairly good match between what we've been observing for the past few decades and what we see in the model, we can possibly then use the model to see how these cyclone impacts may vary in the future. So first up, we're going to be looking at differences in storm count. And so in this study, we're looking specifically at intense cyclones, which we have defined by using a pressure threshold. So in our AERIFY reanalysis, we used 984 millibars to define the central pressure of an intense storm. Then we performed a series of sensitivity tests to kind of scale for the CSM resolution and found that 986 was an equivalent storm pressure. And so on the far left here in these bar plots, we're showing the mean number of detected storms from the 40 different ensemble members that I analyzed. And we find that overall, CSM2 tends to have more of these intense storms in the Arctic on average, a little over 100 compared to about the 90-ish in the Era 5. However, since we're considering cyclones that impact the sea ice, we then take the census of storm and filter them through a series of tests. And the first one in this blue is simply, does the cyclone interact, come close to even touching the ice edge, just its general location. And in CSM2 large ensemble, that removes about 2/3 of storms compared to the about 30% in Era 5. And then the remaining breakdowns with characteristics such as we're looking at storms that have a 2-day duration and go over the marginal ice zone. Those filters are fairly similar between the two data sets. But because there's this large decrease in storms that don't reach the ice edge, overall, there are fewer ice interacting storms in CSM. And that's shown in these maps here, which show the frequency of sea level pressure points below our minimum. And we can see that there's this maximum in Era 5 to the east of Greenland that is well represented in CSM2. But then there's also this maximum in the central Arctic that doesn't quite show up in the model. So this is just one way of showing that there's not as many of these ice interacting storms in CSM. But then when we look at the impact that the storms that do interact with the ice have, we find that they're slightly too large of a negative impact. And so these blue lines are the same mean lines that we showed in that kind of crazy spaghetti plot from before. And we see in the same 4 month and decade groupings that the mean spread of the ensemble members is consistently lower than what we would expect from the changes that we saw in our satellite sea ice observations. Particularly in the early summer, we saw this kind of flattening out of the impact in the observations, but in CSM, there's this kind of continued decrease in area that we maybe wouldn't have expected. And so 2 things that we looked into to kind of begin to explain these differences is that although we have our mean trends up here, each of these ensemble members does have a bit of variability. So we have plotted here is the fraction of storms in each ensemble member that decrease the MIC ice area. And we see, again, particularly in the early summer, very high fractions where most of these storms are decreasing the ice area, more so than we would expect from our Era 5 storms. Kind of the same thing in the late summer where we would expect about, close to half each, but we see a much more greater fraction of these ice decreasing storms. And then the other thing we looked at, if we recall back to our case study from the beginning, there was this steady SST increasing trend. And so what we find, again, in the early summer, most of the storms have that increasing SST trend in a much higher fraction than, again, we would expect from our Era 5 storms. So this just really highlights the importance of the ocean environment in understanding some of these cyclone impacts. And so what we have now is that in the model, we know that there are too few storms that have too large of an effect. And so now if we kind of just zoom out and look at the total impact altogether of accumulated cyclones, we see that the ensemble spread does capture this total change in area. So these 2 biases do produce a similar net effect on the ice, particularly in the more recent decade. We see that the ensemble mean is quite similar to the impact from the Era 5 storms. Earlier in the satellite decade, the model still may be overestimating these negative effects just by a little bit, but I think it is close enough that we can go ahead and move on to looking at future decades. And so what we have here is we have 5 summer months from May through September for 12 decades, broken up by latitude band. And so this top plot shows the total amount of ice area in the marginal ice zone. And we can see, as kind of we would expect, this sort of northward progression and expansion of the MIZ throughout the summer season in kind of the current and recent years. And then it sort of begins to taper off and weaken as we move into some ensemble members showing like an ice-free Arctic, and we see, particularly in these late summer months of August and September, just no more ice left over. And so despite the fact that the total number of these intense cyclones are predicted to increase, particularly in these lower latitude bands in the future decades, the sort of limiting agent here is the amount of ice available for cyclones to interact with. So we see a steady decrease in the amount of marginal ice and interacting storms in these later decades. And so just to kind of spatially show this, we have our early satellite era at the top, and just kind of to revisit some previous results, we see the sort of intensification of ice decreasing through July, and then it kind of tapers off to our slightly positive September outcomes. But then if we take July, for example, and look through 4 decades into the future, we see from the early satellite era into present day, as the marginal ice zone expands a little bit and becomes a little bit more susceptible to these changes, we see a strong intensification of the cyclone impacts. But in the near future and far future, when there just simply is not the amount of available marginal ice, we see a weakening of the cyclone impact into these future decades. And then, so if we then step ahead and fill in kind of these remaining spaces, one last interesting point I'd like to share is if we look at the months with the largest decreases in ice area, we see in present day that is July. But if we step 40 years into the near future, we see these impacts kind of shift into June and then into May as well, just as we see that marginal ice zone becoming more susceptible to these changes earlier in the year. So I have my summary here, and I will take any questions. I'll stop sharing my screen so I can see.
All right, question in the room or online? Alex? And we're bringing you up.
Yeah, thanks. First, Claire, thank you for a great talk. I love your figure work. Just getting back to that question that you had with having fewer storms in CESM than ERA5, but having a bigger impact on the sea ice. When I hear that, I think at first blush, well, there's either something different about the storms in CESM or there's something different about the sea ice. Like the sea ice might be thinner, maybe more susceptible to the storm impacts, or maybe the storms are more intense, or maybe the storms are less symmetrical. I was wondering if you looked at any of those things.
Yeah, so just first, I did look into ice thickness, but because we are looking specifically just in the marginal ice zone where it is a lot of that first year ice, there isn't like a super strong tendency with thickness. I don't recall there being any noticeable differences in the overall pressure differences in the storm. So I think the main differences come about through maybe like the ocean environment. I did show the changes in the SST. So there might just be this overall warming in the ocean that's causing that during the storms. Yeah, so that's kind of my first glance through this.
Okay, no, thanks. And if you ever get more details, I'll definitely be interested to read about it.
Cool, thanks.
Anyone else? One more question? David?
Yeah, the room mic's on. Can you hear me?
Yes.
Great, thanks. Yeah, going back to the first half of your talk, and maybe I missaw this, but it looked to me like the recent decade September storms had a larger impact on increasing ice area than the prior decade, the 80s that you were comparing with. And I was wondering if you had sort of a mechanistic explanation of why that might be.
Yeah, that's something I'm kind of looking into right now, is looking into these sort of month by month changes in the ice cover. So I don't have a super good explanation for that right now, with the only caveat being at that point in the summer, there's already been a lot of breakup and advection from these storms previously that maybe the effect of these September storms are, kind of swinging in the other direction at that point. But yeah, that's something I'm kind of working through right now to look at that.
All right. Thank you, Claire. All right, so we're going to move on to the next talk. I don't know which of these is working yet, but we have Xiaochen Wang, and he's going to talk to us a little bit about Mosaic.
Good afternoon, everyone. So in the next 15 minutes, I'm going to talk about recent work we did doing some sea ice thickness simulation during the Mosaic period. And different from the full flat coupled models of the result from two previous speakers, I'm going to dive into a column model in size called the ice pack. And before we get fully started, talk the recent work, I'm going to kind of review the work I presented in the workshop in 2024. That's a preview of our present work. In that work, we kind of tested the several schemes, BL99, multi-layer for thermodynamics, CESM, LVL on top for melt pond. We use the sorry, I try to pinpoint some of these.
Let's see. Hang on.
Okay, my fault. Basically, I tested 2 thermodynamic schemes and 3 melt pond schemes, and 2 for the Mosaic period.
Here we go.
The idea is to use the atmosphere forcing, to use the sea ice, to use the atmosphere forcing from the operation, to use sea ice operation from the operation, and only leave the ice, sea ice as a variable. And we tested 2 schemes, 2 thermodynamic schemes, BL99, multi-layer, CESM, LVL, top, for melt pond schemes. There are 6 combinations of them. Because there is a missing gap in the operation, so we have to do the simulation for 2 periods. One is for the winter of 2019 to spring of 2020, where the sea ice grows. The other one is in the summer of 2020. So the main conclusion is that during the winter time, the sea ice grows very well. However, there is overestimate from the sea ice growth because there is the snow sea ice conversion is kind of extensive. During the summertime, the sea ice thickness tend to be much thinner in the simulation because we have a lower albedo. And during this time, we do the simulation for 2 periods since there is gap in the operation. So in current work, we try to do a full length simulation from November 2019 to October 2020. For those who do not follow the Mosaic, it's a field experiment occurred in 2019 and to 2020. Some of you in the boat and doing the actual operation. There are a lot of papers cover different aspects of this one. For us, we use atmosphere forcing, atmosphere operation from Central Observatory 1 and Central Observatory 2, oceanic operation from 2901, which is buoy, and sea ice thickness operation, which is thermistor, from 2019 T66, which gives us the sea ice thickness and top melt and bottom melt. In order to do a full length simulation, we have a problem here, how to fill the gap in the middle when there is no operation. What we try to do is we compare the MOSIC operation with the ERA5, the latest reanalysis, and then if it agrees well, then we use the ERA5 instead of 2P, instead of to avoid the gap for the operation. That's a comparison for UV, temperature, humidity, precipitation, short wave, long wave. From figure, you can roughly say it agrees pretty well. It's the comparison is for hourly data. So you can also notice the gap in the late May, early May to late June, late July to August. Here is a more detailed comparison. You can see for wind, it's the MSE is about 1.4 meter per second, and 2 meter temperature, about 2 to 2.5 degrees. The large difference occurs for the precipitation. And also you can check the correlated coefficient, all of them about 0.9, which are significant at 95% level, except the snowfall and precipitation. So then the next step, we will use the atmospheric forcing from EI5 and atmospheric reanalysis from EI5 and the temperature and salinity operation from the MOSIC and to force the ice pack with the column model. Here is setup. We use the ice pack 1.4.1. We only use thermodynamic scheme multi-layer, and we try to, since in the first simulation, we identified there is a overestimation of snow ice conversion. There is a in 1.4.1, the snow redistribution scheme it was installed. So we try to test those schemes. There are 3 snow redistribution configurations. We tested. One is no one. We do not use any of the schemes. There are box scheme, and there is no drag scheme. Those references are there. And then 2 melt pond schemes, one top and LVL. So the combination is DO6. Then we started with the operation for CI thickness, snow depths, pond fraction, and pond depths with the operation. This figure summarize our simulation. The black one is the operation. Okay, this one can do. Okay, okay. The black one. Yeah, good. The black one is the operation, the CI thickness. The color one are the 6 combinations. The simulation start from November 2019, end of August 2020. You can see before May or middle of June, you can see basically the 6 color lines are kind of in 3 groups. The green line agrees the best. The green line, there is a yellow line behind the green line. This one is the bulk snow redistribution scheme. The blue one, which agrees, the blue one kind of have overestimation of snow thickness. This one, without using the any of the snow redistribution scheme, and it's similar to the result we had, we presented in the 2024. The other snow redistribution scheme, which is a kind of light blue one and the red, and has even much more overestimation of the snow thickness, the red one. That's during the snow growth season. During summertime, when melt ponds start to form and snow start to melt, you can see these lines kind of diverge. You can roughly see the top and the LVL has some influence on them, and we will do more analysis for different terms to understand why. And those are into 3 groups, still the same experiment. we separated into three schemes based on the snow redistribution configuration without any of the snow redistribution, the top one, the bulk, and the snow drag one. If we check all the terms which contribute to the CI thickness change, the positive is the increase, the negative is decrease. Basically, two large terms. During the winter time, it's the snow and ice conversion, which is a green one. During summertime, it's the melt from top melt, two large terms. Other terms contribute a little too, of course. And you can see the slight difference between the top scheme, which is the solid line, and the dotted line is the LVL scheme. They are very different during summertime. And also, we can roughly see that you can see no without snow redistribution, and the top one without snow redistribution, and the bottom one with the snow eye drag snow redistribution. The green one seems to be larger, meaning that it has a more kind of snow ice conversion. These are summarized in here with kind of detailed numbers. Two large terms, snow ice conversion and top melt. You can see the bulk one, the second line, the bulk one has relatively smaller snow ice conversion. That's why it does not overestimate snow thickness that much, CI thickness that much. And during the top melt one, you can see the simulations with top scheme seems to do less melting and maybe higher albedo, as we can demonstrate later. And eventually, the top one, the one with top scheme and the bulk scheme, from the RMSE, it seems these two agrees well, but we can see from the tendency, the growth and the melting, it seems top and plus bulk scheme seems to be better than the other combinations. In fact, those comparisons are for CI thickness. That if we dig deeper, there is one scheme that actually can change the snow density. However, in operation, I didn't find the snow density data yet. So we compare the snow depths, and you can see the green one and the blue one. These two are kind of on the same trend. The red one actually is the one with the snow drag, snow redistribution scheme. From this one, maybe we will say that there should be the red one should agree the operation better because it has less snow depth. In fact, the density was not here, not in the picture. The third snow redistribution scheme, snow drag, in fact, can change the snow density. And another thing we can see, we can analyze this is we check the snow loss into the ocean. This gives us a more clear picture. We can see actually the bulk scheme, snow reduction scheme, and the loss more snow into the ocean, and the less snow converting to the sea ice. That explains why the bulk scheme agrees better with the sea ice thickness operation during winter time. That's the story for the winter and springtime. The other thing is that what happened in summertime when the simulation tends to underestimate sea ice thickness. We analyze the radiation, and for 3 snow redistribution configurations and 2 melt pond schemes, different lines, you can see the different lines are the net long wave, net short wave from MOSIC and from the ice pack. Let's draw your attention to the light blue one and the pinkish one comparison, or magenta comparison. You can see there is a gap in the middle, and if we use the top scheme, it seems during summertime, the solar net short wave radiation seems to agree better with the operation. For LVL, it seems it's a little bit larger. For albedo, tells a similar story. The observed one is two black lines, one with a gap in the middle. We can see that with the top scheme, it has higher albedo. The three lines with a slight higher with the light blue, yellow, and magenta, and the light what's that? The blue, green, and red one is the one with the LVL. It has this one has smaller albedo, right? Yeah, it has a smaller albedo. Yeah. In terms of melt point, we separate into melt point fraction, melt point depth, and compression. The dot one is the operation. For a field experiment, all the yellow lines are for the operation. We can see roughly. For top one, it seems, at least for the melt point fraction, it seems maybe agrees a slightly better. Yeah, and consistent with the stories we talked about before. So that's kind of summary. We kind of tried 2 melt point schemes and 3 snow redistribution configurations without snow and bulk and snow drag. Then we kind of identify during the winter, springtime, there are extensive snow ice formation without using the snow redistribution scheme. However, the 2 schemes we tested, it seems bulk seems to be better. During summertime, ice pack tend to underestimate sea ice surface albedo and result in underestimation of sea ice thickness at the end of the simulation. Next is our future work. So the snow density were not in picture yet. Since there is one figure we demonstrate that the simulated snow thickness are kind of very different from the observed. That's only for the sea ice snow thickness without density included. Confused? Okay. Say it again.
The noise, we don't know where that came from.
Oh, okay. Maybe I hold it. Okay. In fact, the long-term goal for us is try to identify some of the processes and also those parameters that need to be adjusted. We try to use adjustment method to adjust this and make it more generalized. So if you have questions, here is my email. Thank you.
All right, do we have time for one question? Melinda, we'll turn on overheads.
Is it on? That ask?
Yep.
Okay. Well, thank you for sharing those results. It's really nice work. And you were comparing to Mosaic buoy data, is that right?
Yeah, there is two. One is the temperature salinity one from ocean. The other is semester, the sea ice buoy, which observe the top melt, sea ice thickness, and the bottom melt.
Okay. And I think this might be an idea for future work, but do you have any interest in looking at the in situ surveys that were done over many kilometers of snow depth, ice thickness, and melt pond depths?
Yeah.
That might be interesting to compare.
Yeah.
Thank you.
Is there a density operation?
I think people are putting together a snow density time series, and Amy McFarland would be the person to contact for that.
Thank you.
Thank you very much. Overhead mics are on. So our next speaker is Laura. She is here at NCAR.
Although I could try. While they look for that, I did download. I also have my computer for these. I guess I didn't have a number.
Here. Get your
It's
computer.
right here. Yeah.
So there won't be anywhere.
We're going to switch gears just a little bit here. I will try to make it not too slow because I know that there are coffee and treats waiting for you and we're getting kind of late. If you have questions, I recommend writing them down because this talk is particularly pertinent for the discussion that we have for this afternoon aimed at science and society. And so if we don't have time for questions now, we could have some discussion this afternoon. And I'm really hoping that this stimulates some discussion. And first off, a little apology for any of those. Great. Those of you that were at my CGD exchange talk last week, this is the same talk. So I won't take it personally if you fall asleep. This work, although I'm the only one presenting it today, it's definitely a collaborative work with a large range of people. The primary collaborators are listed on this slide, and I want to do a particular shout out to Merle Appitzingok and Brian Rocock Jr., who have been very generous in sharing their stories, their experiences in their communities. And this kind of began as a project in many ways when Marika and I had a paper that was published in 2020 that basically said, hey, the statistics of the Arctic climate have changed so much that it's no longer in the same climate. It's in a new climate. And it was a paper published in Nature, got a lot of press, got a lot of coverage. It was pretty exciting. I was pretty proud of it. Like, wow, this is pretty cool. If you go to an Arctic community and say, hey, the Arctic has been changing. This paper said that 5 different large ensembles from different models all statistically agreed that the statistics describing sea ice was different enough in 1990 for the Arctic to be in a different climate. And that was pretty big news in the scientific community. But if you go to an Arctic community and tell them this, and if they're comfortable around you, they will laugh at you and say, it took you a quarter of a century to find this out? You know, it's like they have been experiencing tremendous, dramatic, and rapid change in the climate and the conditions. And so much of this work is guided by my own motivation, as well as those that have been working in these projects that I've been involved with, in better understanding what do we do as climate model scientists that can be of service to communities. And likewise, how are communities experiencing climate change that can help guide our research and climate models? And how can we work together, share our stories together, and learn from each other such that we can help communities and they can help us in our research? A lot of this work requires, Jackie Catalina Schaefer has been involved in a couple of these projects, and her grandmother has a saying that you have 2 ears and 1 mouth for a reason. And I would just like to put out there, when you try to do work with communities with a different background than your own, it's a very important thing to remember that you're there not so much to tell as to listen and learn. And that's a vital part of this experience. So I'm going to talk a little bit about climate change in the Bering Sea, Bering Strait, Chukchi Sea regions from 2 perspectives. From mine as a climate model scientist and how we communicate that, and how communicating some of these stories from communities about how it's been changing. This region has been populated by communities for about 15 to 18,000 years. So for 15 to 18,000 years, communities have been thriving in these communities in this region. And the communities that are here are along points where they can access food. Now, this region has a very high marine productivity. In the spring, as the sea ice retreat, leads open up, and they tend to open up in pretty much the same places, give or take a little bit. So these leads provide routes for migration for whales, walrus, seals, fish, and birds also that follow them, and they're really good sources of food for these communities and have been so for thousands and thousands of years. Right now, things are changing. Here on the right, I'm showing a plot of the contours of where you're getting at least 3 months of sea ice a year, with the dark lines indicating from the satellite record, 1979 to 2020. And then the dashed lines are from the CESM-1 large ensemble projected in the future in this area. And basically at the the latter 1979, beginning of the satellite era, you were getting 3 months or more of sea ice in the south of the Bering Strait into the Bering Sea area pretty reliably most years. Now, many of those places are not getting sea ice for 3 months of the year, and the future projections from the large ensemble are that by the end of the century, as far north as Utqiagvik, you may not be getting sea ice for more than 3 months of the year. And it seems in Brian and Merle, the individuals who contributed the community observations are from Gamble and St. Lawrence Island. That's the red dot in the southernmost point. St. Lawrence Island is a very big island. It's actually closer to Russia than it is to mainland Alaska, I believe. And they're saying that every year, it's like they're chasing the ice north. Ice for hunters, for walrus, for example, ice serves as a platform for walrus to breed, to raise their pups, as a nursery, to leave their pups while they go for food below, as a resting place. And you don't want to hunt walrus when they're on land because they tend to stampede, they panic and stampede. Female walrus are around a ton, male 2,000 to 6,000 pounds. And they kill each other when they stampede. And of course, they would kill you if you're trying to hunt them. So you try to get them on ice. So as that ice is retreating further north, these communities are having to travel further north to get to the walrus. And that means oftentimes that they need larger boats, they need more fuel. And then weather conditions, meteorological conditions also play a role in hunter safety. As you get more open water, if you have a storm, waves can become bigger, can become less safe for hunters to travel out there. And likewise, if the boats need to be out longer, there's more implications for weather. You have to look at the weather forecast longer out than you might if the prey is closer to you. Here's that same figure, and now I show a time series near Gamble on St. Lawrence Island, and that time series is just showing the number of ice-free days plotted from the CSM1 large ensemble. The mean is in the dark solid line, and then the range in the shading around it from 1920 to 2100. The red lines are from the satellite observations, just the number of ice-free days. When we show this figure to communities, this often starts a lot of conversation because they can say, oh my goodness, yeah. In the past, they've often said that winter is when the ice arrives. As they're looking into the future, and even now they've had some winters where they don't really have winter. The ice is not arriving. Ice also plays an important part in processing meat and accessing it. So those communities that hunt whales, they are hauling the whale out on top of the ice to butcher it. And if the ice is not thick enough, there it goes. And it's not safe. Or if the ice isn't going out far enough to get to where the whales are. Likewise, land-fast ice for these communities is very, very important. I didn't even know this. We're having a casual conversation, and one of the women there from, I can't remember exactly where, but she was saying they have to have about 10 days, I believe, of land-fast ice in June, July to properly process the seal meat, because the seal meat is hanging out there to dry. It has to be close enough to the community that can easily access it and also defend it from polar bears. And it has to be cold and dry. And if they don't have that land-fast ice, they don't have the place to process it. So that's another important thing. And in some years, they're seeing more years now where they are not getting enough food to feed the community. And by the way, these communities, the only way that you can get outside goods in, such as groceries that might be from a grocery store, for example, is you have to take them in by plane or by boat. There are no roads to these communities. There might be a road within the community, but not from the outside. So it's not like they can go to the grocery store and get food when they didn't get enough in their hunt. Storms are playing a significant role in changes along here. Coastal Alaska, particularly the northern coast right now, is seeing some of the largest rates of erosion in the world. You can get these coastal erosion events when a storm comes in. If there's not very much sea ice, you have a longer fetch, you get more energy in the waves, more turbulence, and you get more destructive power. And the waves are then interacting with the permafrost and thawing the permafrost. And that water will thaw that permafrost a lot faster than warm air will. And these sea lice, you're getting tremendous coastline erosion and loss, and that's affecting infrastructure. Entire communities are having to relocate and figure out where to relocate. Now, it turns out that the Bering Chukchi Sea area is also considered a hot spot when we look at future projections of Arctic cyclones. Cyclones in the winter that reach the Arctic, December, January, February. On the left, these are results from the CESM2, just showing storm tracks from 2015 to 24 on the top one, and in the bottom one projected on in 2085 to 2094. These are winter, December, January, February. And just, you can easily see that there's a large number of cyclones, an increase in the number of cyclones we expect to reach this area. And at that time of year, there will be less sea ice and they will be less more destructive. Another thing that communities are very concerned about are algal blooms. Now, algal blooms, particularly harmful algal blooms, there's still a lot we have to learn. We can't predict them very well. Many of these communities who once again have been living here for 15 to 18,000 years have not experienced harmful algal blooms. They don't have a historical reference for these algal blooms. On the other hand, the ocean temperatures are warming, sea ice is retreating, and we know that the risk of a harmful algal bloom increases dramatically when you get ocean temperatures above 8 degrees Celsius. So in the right, I'm showing a point near the Shishma Reef region, which is highlighted by that star in these figures on the left, of ocean temperatures, surface temperatures in the time series as a function of time in August near Shishma Reef from the CESM1 into the future. And you note after about 2045 or so, that on average, they're above 8 degrees Celsius. And then on the left, I'm showing ocean floor temperatures on the top and ocean surface temperatures on the bottom. It's been colored. This figure is courtesy of Kristen Crumhart. It's been colored so that the red colors are 8 degrees or warmer and the blue are 8 degrees or colder. And so the temperatures themselves are going to provide an environment that will be more conducive to hazardous algal blooms. And likewise, in the Chukchi Sea, in recent years, they've discovered these cysts that are in the sediments. And we don't really know if warm temperatures are going to lead to a massive bloom, but they might. There's a tremendous risk. The concentration of these cysts is the largest they've seen anywhere in the world. And it has great potential to affect communities in that way. And then on our last figure, another way of looking at sea ice concentrations on the right is a point near Gamble on St. Lawrence Island. And this figure is showing sea ice concentrations as a function of month on the x-axis and year on the y-axis using the extended observational data set of Walsh from 1850 to present, and then the CESM1 from 2021 on to 2100. The darker the color, the less the sea ice. So the really dark blue is no sea ice, ice-free. The really white color is sea ice, ice pack, 100% concentration, and in between. And once again, another visual way of showing that near Gamble, up until about 1950, they were often having sea ice for at least 6 or 9 months of the year. And now, even in 2021, they aren't even getting it for half of the year, and that is projected to continue along. Now, in these communities, food storage is also an issue. Historically, they have stored much of their food in these earthen cellars, and these earthen cellars are dug in the earth in the permafrost. The permafrost keeps them cold. They sometimes harvest sea ice, so land ice, to put in there to keep them cold longer. And these they are falling into disrepair partly because they're getting more rain events, and the rain will thaw that cellar and thaw the permafrost. Warmer temperatures will thaw it, and they're having food storage problems. And this really relates back once again to having food throughout the year, because a walrus, you think a bull walrus is what, 2 to 3 tons? You can't put it in a freezer. You know, a refrigerator in your house is not going to hold the meatballs that they make out of this. They need a larger storage space. Or likewise, a bowhead whale does not fit in a small space. You need a large space. And these communities are used to, sometimes they will have a bad year, and this meat can help them survive for a year or two without a successful hunt. Anyways, this figure is kind of meant to be my, like, I'm used to doing science where you have a hypothesis and you have some methods and you prove something is kind of linear and you deconstruct. And this work is not linear. It's convoluted, it's complicated, it's really fun, but it's also, everything is related. And I hope that we have some good discussion this afternoon on just ideas about how we can reach out to communities, how can we tell our stories such that the dialogue ensues, that they understand what we can do and we understand what they would like and need. That's it.
All right. Thank you, Laura. So I think we have time for a question or two, and then we're going to go to break. Anyone in the room? Anyone online? Anyone online? I think everyone wants their break. So we'll be back here at 2:30. Our whole discussion this afternoon is science community. It doesn't necessarily mean just these communities, but science for society as a whole. So hopefully we'll come back to this at least somewhat then. So we'll see you people online in about 18 minutes. All right, so we're going to restart, and we're going to continue in some of these science for society aspects of things. And our first speaker is going to be Courtney Payne from the University of Colorado.
And NCAR, thank you.
And NCAR, I'm so sorry.
Thanks so much. I'd like to start by thanking my collaborators, Nikki Lewandowski, Marika Holland, Kristen Krumhart, and Alice Duvivier. So phytoplankton are single-celled plants that drift in the surface currents of the ocean. And they're important because both they provide the basis of the marine food web, and also because they take up carbon dioxide and produce oxygen. So they are really important to the global carbon cycle. And this is an image of a phytoplankton bloom occurring off the coast of Norway. And you can see sea ice in the top right corner of this satellite image. So this kind of demonstrates a lot of how we think phytoplankton blooms happen in the Arctic. They typically occur right around the timing of sea ice breakup and retreat. And that is because, of course, the Arctic is a highly light-limited environment. The polar night means that there's no light availability for much of the year. And sea ice also limits the light in the surface ocean and thus the ability for phytoplankton to grow. So it's only around the time of breakup and retreat that you get much primary production, and that leads to a short, intense burst of primary production, which is, of course, pretty important to the ecosystem. This big bloom allows for the growth of a lot of zooplankton, such as these copepods, which in turn feeds the marine ecosystem, including charismatic upper trophic level organisms like this whale. And as we, due to climate change, we've seen these phytoplankton blooms shift earlier in the year. And that earlier timing means that the blooms are happening under slightly lower temperatures than they used to. And those lower temperatures prevent the growth of zooplankton, which means there's maybe less food being available in the ocean, and thus less food available to those upper trophic level organisms. So my collaborators and I were really interested in assessing how Arctic phytoplankton blooms might be changing under climate change. And I've already told you that there's a pretty big sense that they're moving earlier. But the start of the phytoplankton bloom, we don't have a good sense of how much earlier that is happening, as well as how much of that earlier shift might be due to climate change. There's also a big open question about how much shorter or longer the bloom might be in the future. And finally, a sense of maybe changing importance of the bloom. I've talked about these Arctic phytoplankton blooms as a burst of primary production with biomass really concentrated in the bloom period. But there's potentially a sense that biomass might be less concentrated in the bloom in the future due to fall blooms, and maybe that might mean that there's kind of a low availability of food spread through a larger part of the year. In order to answer these sorts of questions, I of course have to start by defining the Arctic phytoplankton bloom. So we used carbon-based phytoplankton biomass to set our definition of the bloom. And we determined that the bloom started on the date when biomass increases above 25% of the maximum. And it ends on the date when biomass first declines below 25% of the maximum. And thus that the bloom length is just the number of days between the bloom start and bloom end. And we rolled this definition of the Arctic phytoplankton bloom out across the Community Earth System model, and specifically the large ensemble. So this is a set of 50 ensemble members that all have the same climate forcing, but have slightly different initial conditions, which means that there's different realizations of Earth's internal variability in every year. And to assess the impact of climate change on bloom dynamics, we compared the means for 1970 and 2100 across these different ensembles, or ensemble members. And this allows us to isolate the impact of climate change on changes in bloom dynamics and kind of ignore the effects of internal variability in any given year. So I'll start off by showing you how the start timing has changed. So we took, for this analysis, we took 1970 and we took 2100 start timing and subtracted 1970 from it. And values in red mean that 1970 had an earlier start time, while blue means that 2100 has the earlier start time. And here's a map of the Arctic. We can see Alaska, Greenland, Russia, and Norway over here. And as you can see, it's a very blue map. That's because, of course, the phytoplankton bloom, as I already told you at the start of this talk, is moving earlier. You can also see some places where there's stippling, and that indicates that there's no significant change over this period. So across the Arctic as a whole, the bloom is moving about 34 days earlier by 2100 as compared to 1970. And I haven't shown you evidence of this, but you can see that a lot of those changes are in the first year sea ice zone at present. So a lot of the changes are really isolated in areas that are currently first year and maybe in the future will be ice-free. Okay, so we'll all now look at the end timing of the phytoplankton bloom. Again, if the end shifts earlier in 2100, the map will be largely blue, and it looks pretty uniformly blue across the Arctic. So in this region, the bloom is ending about 19 days earlier on average. And you'll notice that this is kind of a more uniform change than we saw with the bloom start timing. Much of the Arctic looks kind of a similar color in this map. When we look now at duration, it might not be a surprise that if we have a much earlier bloom start and a slightly earlier bloom end, for much of the Arctic Ocean, we're seeing an increase in the length of the bloom, which is about 14 days longer across the Arctic in 2100 than it was in 1970. Okay, so the next question I said I was interested in looking at was changes in the importance of the bloom. And I assessed this by looking at the proportion of productivity that's concentrated in the bloom as a proportion of the total annual production. So yellowish colors indicate that the bloom is really highly important. It's most of the productivity for the year is concentrated in the bloom, while blue indicates that the bloom is a relatively unimportant contributor to total production. So in 1970, we can see that in the kind of southernmost places, in this image, there's a pretty low importance of the bloom, particularly along the west coast of the US and south of Norway. But in the central Arctic, the bloom looks really important. And when we compare this to 2100, we can see that the central Arctic maintains its importance, but the southern latitudes look really substantially less, the bloom looks substantially less important at these latitudes. And that's also true in the Barents Sea and the Chukchi Sea, which are two of the most important inflow regions into the Arctic. So a lot of water is moving into the Arctic through these two gateways. So this indicates to us that the bloom is losing its importance in the future in the subarctic as well as on these inflow shelves into the Arctic. Okay, I've showed you a lot of kind of pan-Arctic figures that I think illustrate some of the changes we anticipate in the bloom. But it's a bit hard for me to gain a sense of what these actually mean for any given location. So I'm going to show you a couple representative places. And I'll show you 1970 and 2100 daily primary production, both a mean and a standard deviation across these ensemble members, as well as the start and end timing for the bloom. I'll start with the Bering Sea, which is a place that is occasionally sea ice covered in 1970, but has no sea ice cover at all by 2100. And at first glance, these plots of primary production look really similar between 2100 and 1970. Maybe 2100 certainly has a higher peak and maybe declines a little bit more rapidly following that peak, but they look quite similar at first glance. It turns out that the start timing of the bloom is unchanged in this location because sea ice loss kind of meant that there wasn't, or the sea ice cover in 1970 means that there's not too much change in the light available in the surface ocean. But the end is shifted earlier by 40 days over this period. So overall, we end up with this shorter bloom and also with less productivity concentrated in the bloom. More is kind of happening in this long tail following the bloom. The next location we'll look at is the Chukchi Sea. This is a place that has occasional perennial sea ice in 1970, but is seasonally sea ice covered and even ice-free in some years by 2100. And here the 2100 and 1970 blooms look super different. There's no confusing the two. In 2100, the bloom is starting substantially earlier, about 60 days earlier than in 1970. But you'll see that it's quite variable, and that's because in some years there's ice-free conditions, and in others it's covered with first-year ice. The end timing is pretty much unchanged. So overall, you get this earlier and longer bloom that's also a bit more variable. There's also really no change in bloom importance. It produces the same proportion of total annual production in 2100 as in 1970. But that means that there's lower daily mean productivity during the year. Okay, the final location we'll look at is the Central Arctic. This particular place is 84 degrees north, so it's really super high Arctic. And it was covered entirely by multi-year ice in 1970, but by first-year ice only by 2100. And here we can see that the bloom start timing has shifted a little bit earlier in the year. The end timing is not super changed. So overall, you're left with a slightly longer and earlier bloom. But of course, the thing that's most notable about this figure is that there's far more annual production as well as bloom productivity in 2100 than there was in 1970. This is a place where production is increased by about threefold over this period. So overall, I think this work demonstrates a couple interesting things about the bloom of the future. First, that Arctic phytoplankton blooms will be generated earlier in the year in the future, and then in much of the Arctic, blooms are also going to last a bit longer. It also shows that while the bloom in the Central Arctic is going to remain a concentrated source of production, the bloom is reduced in its importance on inflow shelves into the Arctic and in the subarctic. And I think this work will likely have some really, these changes will likely have some really important implications for trophic transfer as well as for carbon export. These are things I'm looking into next, and I'm really interested to learn more. Thank you so much.
All right. Questions for Courtney in the room? Online? Keith?
Thanks for the presentation, Courtney. Great. Did you look at the bloom dynamics of separate plankton groups in the model, or is this just the total?
Yeah, this is all just total primary production. In both years in the Arctic, diatoms account for like 93% of the phytoplankton functional type productivity. But I think the changes in species composition are really interesting. And right now I'm using a 4P2Z version of the model to kind of start to dive into the relative changes in coccolithophores and small phytoplankton as well as the diatoms. Thanks so much.
Anyone online or anyone else? Okay. All right. Well, thank you, Courtney. I'm still your mic.
Oh, I thought I was just going to keep talking. I prefer not to.
All right, you're stuck with me next.
It's not
But I have my phone, so you won't be stuck with me too. I'm sorry. Okay. So I'm the next speaker, and like I said, I have my phone here, so I will not go extra long, don't worry. But I am the first of the afternoon presentations that is going to shift to the other hemisphere. So the next three presentations are going to be about the Antarctic, but this one is also kind of biologically focused. So this is a project I've been working on for a while about the changing Arctic environment and impacts on ecosystems. And it's one that we've been working with some end users, which are non-governmental organizations, to try to bring this forward to the CAMLAR, which is the organization that controls policy around Antarctica. So I'll talk a little bit about that too. The main thing I wanted to point out at the very start is to make sure to say thank you to all the people who have provided input on this. I am not a biologist. I've learned a lot about biology, like how far penguins swim. Wow, they swim really far, but they're usually weird juveniles, things like that. But really, it takes a big group to make all of this happen. So thank you to everyone. All right, so the fundamental question that kind of started all of this is, we have polynyas. I think probably most people here know what a polynya is, but I'll define it just to be sure. A polynya is an area of less ice concentration or thinner ice that's surrounded by more ice or maybe bounded by a coastline. So you can see in this figure here, areas that we've identified polynyas are shown in red. You can see very well here, the darker color means lower ice concentration. And this outline is where polynyas often form. And you can see that they happen all around the coasts of Antarctica. And so what we're really interested in is identifying and quantifying how valuable polynyas are for the Antarctic ecosystem and how might the value of these polynyas impact policy, including for marine protected areas or MPAs. And you can also see on the same figure, these yellow lines, some of them are solid, like here in the Ross Sea, there is a marine protected area enacted there. And then there are several others proposed around the continent, but they have not yet been adopted. So the first thing that we had to do for this project, because we want to be able to look at this in the present and in the future using our model, is to quantify how well CESM can capture polynyas. And your first thought might be, well, it probably doesn't do that very well. And very small scale features, I would say that's true, but we do capture polynya features actually pretty well. So this figure on the left is showing where we identify polynyas from the satellite observations in yellow. And then in red, where we identify them frequently from the CESM. And this is a hindcast, so that we're kind of comparing more orange or red delicious and Granny Smith apples. They're not the same apple, but they're closer. But what you can see is they actually match pretty well where they occur. They're not identical. We don't expect that they would be. But this gives us some confidence that we can actually use CESM as a tool for doing this work. And this is work that's currently in review by Laura Landrum. And I think she's working on revisions now. So what we want to do is quantify across different parts of the ecosystem how important polynyas are. What you can see on the right is a NASA satellite image of the Ross Sea. And as Courtney had in her image as well, you can see this very bright green, and this is a phytoplankton bloom that's happening. And you can see these from space because it's so productive in these seasonally ice-covered waters. So what we are going to do in this study is look across the food chain from phytoplankton, also to krill, which eat phytoplankton, and then fish and penguins, which are predators of krill as well, and try to understand how polynyas affect these different parts of the ecosystem. So what we've done is we've created this Antarctic Ecosystem Value Index, or AEV index. And what we've done is around the whole continent, we're looking at where the NPP, net primary productivity, which is the phytoplankton, where the krill growth potential, where the demersal fish biomass, or where penguin populations are highest relative to the whole continent. We add these up for each region, which are the different management regions. And we find within each management region what area has the highest value of each one of these. So the areas that have the highest numbers are going to be valuable across more parts of the ecosystem. And if it's lower numbers, it will be valuable to fewer areas. I want to point out that we did our best to include management relevant indicator species. So for the Ross Sea Marine Protected Area, emperor penguin nesting pairs, Adelie penguin nesting pairs, Antarctic krill, and Antarctic toothfish numbers are all some of these indicator species. And so we've included those in this index. I want to emphasize too, they're not the only species that are important, but they're some of the only ones we had enough data for to look in the present day and into the future for how their populations or their productivity might change. So these are kind of the input layers that we have for this Antarctic Ecosystem Value Index. So this is NPP, an example of NPP, and where it's very bright green, you can see these areas, and this is integrated over the whole growing season. So where it's very bright green are the most productive areas around the Antarctic continent. Krill growth potential here, which is an empirical relationship that depends on chlorophyll concentration and sea surface temperature. And here the reddest colors are the areas where krill have the most potential to grow biggest over the summer months. The yellow colors here for demersal fish. So we have a fish model that's run offline, but using CESM output called Feisty. And so this is just looking at demersal fish or fish that spend part of their life cycle at the bottom, at the seafloor. And this is an Antarctic toothfish, which are actually fished. So if you see Chilean sea bass on a menu, that's toothfish and they're from Antarctica. And you might want to think about if you really want that Chilean sea bass. But these orange or more brown colors are where there's the highest concentrations of these demersal fish. And then we have emperor penguin and Adelie penguins. And you can kind of see these little magenta dots here. Those are where satellite observations have shown that there are colonies. And what we've done is a very simple exponential decay dispersal, how far they go to forage for food. And then we've added up based on those colony populations, how many penguins can access any given grid cell on the CESM grid. And so where it's more purple, you have more penguins able to access those cells. So here in the Ross Sea, where there's tons of emperor penguins, it's very purple. And here, even though there are some colonies, it's not nearly as purple, partly because those are smaller colonies. And we do the same sort of thing for Adelie penguins as well. So we use that equation I had before. We look at the maximum, we scale each one of these by the maximum over the whole hemisphere and then add those up. And then look by region to find what's the highest value within each of these management regions. And we come up with this AEV index, which we're showing here. And we have it on a scale from 0 to 1 just to make things easier to interpret. But the most important thing to point out is the more blue you get, the higher value a particular grid cell is, and these are CESM grid cells, across all of those ecosystem layers. So a few places really stand out as really high value here. So I've kind of showed them here. We bin these just to help us quantify how much area there were in these different categories. So I'm going to focus on the high and exceptional bins here, which I've shown in the kind of pink, that's high, and then red is exceptional. But you can see that there are a number of these areas around the coast. They really don't take up a whole lot of space, but they often are co-located with polynyas. Not always, but frequently they are. And what we've done for this project is we've then looked at, okay, which of these polynyas are valuable? And of the ones that are valuable, which of those are within marine protected areas? So all these blue stars are valuable polynyas or polynyas that have some of this higher exceptional value area in them that are also within an area that has been proposed as a marine protected area. But there are a few places with these gold stars that have polynyas that have high and exceptional value area that have not yet been included in a marine protected area proposal. And so working with the NGO colleagues, we're seeing these as opportunities for development where proposals could be developed, or here where there are 2 marine protected areas, maybe that could be expanded to include some of the polynyas nearby. One area that we've noted that's really of interest is the Amundsen Sea, where there are no protected areas that have been proposed. This is somewhat to do with the territorial claims around Antarctica that people don't acknowledge, but realistically affect how policy is done there and who's willing to put up the first protected area proposal. And coincidentally, the Amundsen Sea isn't claimed by any nation, and I think that's part of why it hasn't been. So the NGOs are trying to decide, could they encourage a nation, or are they able to try to sponsor something like this? And then we were also able to identify, because the AEV index doesn't actually use polynyas or any ice information within its calculation, we were able to identify this area at the tip of the Antarctic Peninsula that's really valuable, primarily because there are a ton of penguin colonies up there, but it's also really productive. And that's a valuable area, but it's not related to polynyas at all. And we just want to make sure to identify that and acknowledge that it's valuable as well. All right, so one of the things that's the most unique about our index is people have made indices like this around Antarctica in different ways, but they haven't looked into the future and how things might change in the future. And because this uses climate model output either directly or to feed species demographic models, we're able to get a projection. So what I'm showing here is the AEV index for the 2090s. And what we found really interesting, and honestly was somewhat unexpected, is that many of the regions that are valuable today, like here, remain valuable into the future. So you can see that the Ross Sea is still bright blue. The shape has shifted a little bit, but that's okay. The Amundsen Sea polynya is still bright blue. Some of these areas around East Antarctica are still very valuable. And so this suggests to us that if we can protect these areas now, they might be some of the areas that these species could have as refugia because they'll continue to be valuable into the future. And so it would be an area where they could maybe try to weather some of the, pressure from climate change. And this is climate change only. It doesn't include fisheries or anything like that. And so there's, this this suggests that it's really important to get those protections in effect as soon as possible so that those species can kind of have their little area that's as much undisturbed as possible to try to adapt to what's going on with climate change. There are also areas like the Antarctic Peninsula and East Antarctica. What you can see here is that we calculated the AEV index only over the sea ice area. And because the sea ice has contracted so much, there are some areas where there's not any sea ice anymore. And so any ice-dependent species, which does include krill or toothfish, is not going to be able to live there. So that's kind of sad as well. I wanted to point out that while it looks like some of these areas stay valuable, the picture isn't totally rosy. There's still some ecological red flags. So Polynya area itself actually stays pretty constant over time. That's what I'm showing here for these different colored regions. But what we found in these regions is there's less ice and warmer temperatures that could increase NPP, but it decreases the ability for krill to grow too much. It gets too warm and they actually can't live above 2 degrees Celsius. At least that's what observations show right now. The deep ocean temperatures start to get too warm for Antarctic toothfish. Almost all the emperor penguin colonies become extinct except for a few areas, but many of the Adelie penguin colonies remain in the unthreatened category. So that's positive at least. And then another whole side to this project is figuring out how to tell the story about this with the NGOs to get this to the decision makers who actually enact MPAs. So I was at the SCAR meeting in Chile in August, and the CAMLAR commissioner for Belgium, so CAMLAR is the organization it's an international organization that enacts policy around the Antarctic marine ecosystem specifically. But here's what she said. She said, for policy making, it's important to see the whole. Emotion is important. If we as policymakers and as a society as a whole do not understand, do not sense, do not feel what you're talking about, what the impact is and what the dangers are if we don't make decisions for conservation, then we don't take that into negotiations. And so this is really highlighting the importance of being able to tell this in like an emotionally evocative story. And so as part of this project, we've been working throughout with the Pew Charitable Trust, the Antarctic and Southern Ocean Coalition, and Only One, who are these kind of bridge spanners who can kind of go between the scientists and the decision makers. And so ASOC has been able to provide like white papers to CAMLAR and lobby policymakers directly. And Pew kind of supports some of that as well. And Only One really works more on getting information out to the general public so those people can put pressure on the policymakers within CAMLAR. And so we're not directly talking, or I'm not directly talking to CAMLAR or the general public, but I'm working with these boundary spanning organizations to do that. And so what we're working on right now, what we're finalizing, is this web tool with Only One to do visual scientific storytelling and encourage Antarctic protection. And we try to include really beautiful visuals like these that John Weller has taken on some of his various Antarctic cruises. So penguins, Adelie penguins swimming. This is a Weddell seal in a little hole in the ocean. Here's some Adelie penguins about to jump into the water. Things like this that really make people feel and want to encourage their policymakers to enact conservation measures. So the takeaways, the scientific takeaways are that polynyas are really highly valuable in Antarctic ecosystems, and we've been able to actually quantify that directly here. Many of these polynyas are in proposed MPA regions, but there are several highly valuable polynyas that are opportunities for protection, and that the valuable regions in the present continue to be valuable in the future and could be refugia for these species if they were protected. So that's all for me. If you're interested in looking at this website, you can scan the QR code or put this website in on your own, but I'm happy to take a question if anyone has one. Yeah.
I'm interested in how well the CSM might get variability in the polynyas.
Yeah, so Laura did a whole, sorry, Laura. Laura's paper, she has this whole paper about the algorithm to identify polynyas and looking at variability. In the hindcast, I think it does replicate it pretty well within the CESM itself, like the CESM2 large ensemble. Do you recall, Laura, if the variability is pretty similar between observations and our
It
model?
is in the hindcast. Yeah.
Yeah, the hindpass looks pretty similar. And then, of course, we have the free running model, which is kind of a separate beast. Yeah. Yeah.
Are the locations and areas of these polygons are relatively fixed? Or how do they change with the changing?
Yeah, so we thought that where polynyas were might change over time, and what we found is they really didn't. How those polynyas, all those coastal polynyas form is that wind blows off the Antarctic continent, blows the ice away from the coast, and so you get an area that's of open water. And so those areas don't really change over time, at least not up to 2100. And so we do tend to have polynyas in those same areas year after year, even to 2100.
Their area doesn't.
The area actually stays pretty similar over time. The ice within the mean state, we think gets thinner over time. Laura.
I would just add that we do see some decrease in the area towards the end of the 21st century. And I think that's because the sea ice is retreating so much that that definition of a polynya being surrounded by sea ice no longer holds. It's this open water area that ceases to be surrounded by sea ice, even though the area is still open.
All right. I think I have had all my questions. Elio, you are next. So our next speaker is Elio Compitelli, who is visiting us from Australia.
You can hear me? Okay, yeah. So this is the title of my talk, which in the program, they missed the fun. I don't know why. But yeah, this is showing, I'm going to show results of my work now at Monash University, looking at the access to sea ice concentration forecast. So what I don't think I need to sell the sea ice here in this room. We all know what ice is. It is solid chunk of water between the atmosphere and the ocean. So we all love sea ice. We like pictures of sea ice. We like to study sea ice. I guess we are the Just Ice League. But I'm looking at sea ice. I'm not a oceanographer. I'm from the atmospheric science side of things. So what I'm looking at is looking at sea ice from above. So, and in particular, I'm trying to understand how sea ice affects the atmosphere and the atmospheric circulation. So, and we know that it must affect the atmosphere because it's like a layer that is in the interface between the ocean and the atmosphere. So fluxes, albedo, there's a lot of things going on there that's different between open ocean and sea ice. So, for example, this is from two models, eddy height between years of high and low sea ice concentrations. And I do this, no. Yep. So we see that there's a difference there, especially like there's a wave 1 in the stratosphere. But the two models don't really agree very much in the nature of that change. And in this Wacom model, it's like an intensification of the climatology, and in this CM model, it's more like shift, like from the latitude or the longitude of where those anomalies are. So there's clearly a lot of work to be done and a lot to be understood here. So I'm going to use the Access S2 model and run experiments changing sea ice and essentially looking at the atmosphere and how it behaves at different sea ice conditions. The Access S2 model is the Bureau of Meteorology in Australia seasonal prediction model. This model configuration, I guess, for this crowd, what is important here is that it uses this size 111. I know it's kind of old at this point, but it's what it is. And also important for me is that the initial conditions for sea ice concentration, there's no data simulation. So it's just it's initialized with the output of the free running model essentially. There's atmosphere and SST and ocean assimilation. So the hope is that part of that information fits into the sea ice concentrations and affects them. And by the name, you might guess that there was also an Access S1 seasonal prediction model, which was the predecessor. So I'm going to show, as well as evaluating this S2 hindcast, not forecast really, but hindcast, I'm also going to compare that with S1. And really the only difference is the initial conditions. With S1, the Bureau was taking the initial conditions from the UK Met Office. So they decided to use their own in-house initial conditions, just to be not dependent on the UK. And so it's a different, the only difference is the initial conditions. And for example, there are differences in the forecast, some like a bias in SST, some parts are improvement, especially here in the region. As you can see, there's a lot of bias in both models. There's a lot of positive bias here in the Southern Ocean. And in some regions, using S2 is improving, and in other ones, it's getting worse. So let's look at the hindcasts, and especially the bias. So this is the median extent, for S1 up and S2 up and S1 below. And in black line is the observations. And then this is taking the median forecast or hindcast starting at the first of every month. The circles are the initial conditions, and then they evolve. And then the triangles are the same data as the initial conditions, so the first of every month, but forecasted by the longest lead possible. So it's very, we can quickly see that there's a problem here that S2 has almost no ice here. Like there's, especially here in the summer, the minimum is a little bit later, and it's almost no ice. And if we look at S1, which had the same model configuration and the same and difference in the initial conditions, and the initial conditions here are pretty are not bad. Like they start right in with the observations, but we can see that then it quickly evolves and drifts to the model, basically the model equilibrium, which can be estimated by the triangles, which is basically the same as S1, S2. So no surprise here that the initial conditions are important. If we go to here, this is the difference between the forecast and the observations. They're basically the same plot before, but like the observations are on a straight line. And it's easier to see now how the difference between where the model wants to be and when the model actually is at the initial conditions. And for S2, since we don't have explicitly that assimilation for the initial conditions, sea ice concentrations, in many months, they are both basically the same. So here we can see that circles, the initial conditions are basically where the model wants to be. So it's kind of like a free running model without any input from the observations. Now, here in summer or our summer, now there is that assimilation is taking place, so the model is being closer to an observation. So it seems that assimilating data from the ocean and from the atmosphere is affecting it's improving the initial conditions in the sea ice, and we can see that compared with S1, much better. So this is now looking at the spatial view at the monthly forecast minus the observation. So basically the bias at 0 months time, and S1 is basically underestimating sea ice, basically anywhere that there's sea ice. And then in the winter months, there's some underestimation, some underestimation, and in the aggregate sea ice extent, it balances out. And now in comparing with S1, which was before, it's much better as we expect, although it kind of overestimates a bit in a lot of months. That is because the go back, not so bad. We can see here is S2 and S1 both, because they have the same model, have the same ice growth, and it actually has during the winter it grows more quickly than in observations. And so if it starts without the bias, it starts close to observation, then it tends to overestimate, at least in the first month. Whoop, and woo. Now looking at the going to the anomalies and instead of the bias, these are time series of monthly CS extent for S2 and S1, and we can see that it's not really S2 is not great at estimating a lot of the variability. The root mean square error during the common period between the two models is always higher for S2, so that's kind of a problem. And S2 has this very large spikes that goes very large into lower CS extent and then to higher CS extent here in the like new orange in the Antarctic, and while S1 stays more closely to observations. And in terms of now more quantifying the error, this is the root mean square error of CS concentration anomalies for S1 and S2 in different colors compared with a persistent forecast of persistence of persisting the anomalies. And at low lead times, basically every month, if you look at access 2, it's kind of the error starts pretty high due to the lack of data assimilation, and then stays kind of like a climatological error, while S1 started with a relatively low error, and then it quickly goes back to the converges to the S1 error. And if we compare now with climatology, again, we see that climatology always has for longer lead times, so for shorter lead times, persistence that wouldn't make any sense because we wouldn't expect persistence of winter with large sea ice and anomalies in the ice edge to make any sense for summer when the anomalies are going to be close to the coasts. But if you use climatology, then still we don't get, even for S2 in this case, we don't get very good skill. And this is now close look, zoom into the first 100 days just to see, and without the range, and just looking at the different models. And unfortunately, what we see is that basically neither of the two models beats either persistence or climatology, depending on where on the time. So when persistence has more error than climatology, then the other models are still have more error. But this is looking at the whole Pan-Antarctic. Maybe when I went to see, there's maybe some areas in which the model is better than climatology or some other benchmark. So this is the root mean square error computed at longitude slices at 15-degree wide for different months. And well, in February, this is compared with forecast with a persistent forecast as a benchmark. So in February, so forecasting February is relatively easy, especially starting in January, but even starting like in October, November, it's easy, quote unquote, compared with a persistent forecast. This is because the model is forecasting that there's not going to be ice where there's no ice, basically. So that's not great. But we do see that there's some areas like here in the Weddell Sea, in which we do have some skill of this compared with a persistent forecast, which we have relatively low errors even here in the Weddell Sea, even starting like as late as January and forecasting our September or August. So maybe there's some degree of skill in those areas. Well, but anyway, that's how for you today. And have any questions?
Questions in the room or online?
How were you initializing your ocean? So
Yeah.
you had sea ice initialized in one case and with the data assimilation and not in the other, but
Yeah, the ocean is for the hindcast is nudged to the daily timescales to Reynolds 15, and this is done only where the sea surface temperature is higher than 0 degrees Celsius, because apparently if they nudged where they were sea ice, then the model would crash basically, and it would degrade or would degrade the forecast for some reason. Probably.
and it was just nudged for SST, not any deeper ocean.
I think, yeah, only SST.
Anyone else online? In the room? All right. Thank you, Elia. All right. And the last talk is going to be Marika Holland from here at NSF NCAR.
All right. Hi, Cece. She told me not to take offense when she left during my talk. So anyway, good afternoon, everyone. So I'm going to be talking about using simulations from CESM to explore changes in variance and persistence of Antarctic sea ice anomalies. And so I actually wanted to label this what I did on my summer vacation, but this wasn't actually summer. So this is basically what I did on my mini sabbatical where I visited Hobart last fall. And so I fought off dangerous wild animals. I love the signs in Australia. I have to say, you guys have the best signs. And you know, this really hazardous environment that you're being warned about everywhere you go. But I actually also got to do some science. And I wanted to thank Will Hobbs, who hosted my visit and contributed to the work I'm going to show you. And I'll say that I did this work or started on this work back in the fall. And I've had very little time since I've been back at NCAR to actually continue on it. So it's still pretty preliminary and there's tons more to do. So I'd love to get feedback from people, chat with people after the meeting's over, all of that, to try and get some more insights on ways to approach this work. Okay, so I'm going to be talking about Antarctic sea ice. I don't really need to show this image in this room. Huge annual cycle. You know, you can see anomalies that occur in the Antarctic sea ice, of course, are very different by season. And of course, we've also seen really big changes in recent years in the sea ice cover. So this shows the monthly anomalies over the satellite record from 1979. And you can see, I'll see if I can use the mouse without also switching the slides. You know, this recent couple decades look really different in terms of the monthly anomalies. They're big, but they also look like they're more persistent. So we can quantify that. And so this is a metric of a decadal running mean autocorrelation. So it's a 6-month autocorrelation. So this panel is a measure of persistence. And this panel is the standard deviation, just a running decadal mean standard deviation. And so, you know, what you can see by eye on the top plot, you can now quantify. We get this increase in persistence in the recent decades, and also this increase in variance. And some have suggested that this might be indicative of a regime shift in the Antarctic sea ice. And so I think some of the questions that we're trying to address with this work are sort of trying to think about, is this actually a regime shift? Is it something that could just be a factor of internal variability in the climate system? So the questions that are motivating our work are whether or not we kind of see these types of changes in a climate model simulation. And if so, how are those changes expressed regionally? Are there some regions that are more important for driving changes in variance and persistence of sea ice? What are the atmosphere and or ocean drivers of decadal changes in variance and persistence? And what is the role of anthropogenic forcing? Do you need anthropogenic forcing to see these kinds of changes? And I'll say that, again, this is very much work in progress. I think we have some insights on 1 and 2. We're seeing some evidence of interesting potential atmosphere and ocean drivers of these, but a lot of the mechanistic understanding of how those ocean drivers and atmospheric conditions are actually causing changes or these differences in the statistical properties of the sea ice, we need a lot more work on. And again, I'd love feedback on that. Okay, so for this work, I'm using the CESM2 large ensemble. And I just want to note this model has a beautiful Antarctic sea ice cover, which is something that we should not degrade in CESM3. So you can see the annual cycle of Antarctic sea ice area here for the satellite era in observations in red, the model in black. And I mean, this is pretty damn good, right? This is amazing. And then this is the standard deviation as a function of month. And we get pretty good variability in the sea ice cover as well, kind of on large scales. There's, of course, biases regionally and things like that. But overall, this model has a pretty good simulation of the Antarctic sea ice cover. So we can look in this model at whether we see kind of changes in the decadal variance and persistence of anomalies. And so what I'm showing here is this metric of persistence on the left, and then the standard deviation on the right. This is for decadal segments of the CESM2 large ensemble, where we have 50 ensemble members that I'm using. And I'm using the black shows 1870 to 1930, blue shows 1980 to 2020, and the observational range is shown in red. And so basically, you can see that we do get a large range in the variance and persistence of anomalies in the CESM2 large ensemble. It does look like it changes in terms of a climate change signal. That's the only thing I'm going to talk about in terms of anthropogenic forcing for the talk. You can also see that, at least in terms of the variability, this maximum variability that we see in the observations by that red dashed line, we don't really achieve that kind of level of variability in the sea ice cover in the model simulations. But overall, you know, we have these interesting and quite large variations in the variance and persistence of anomalies. So again, it can be a useful tool to look into some of these research questions. Okay, so what we did next was to basically do some composite analysis to try and understand what's driving some of these differences in variance and persistence. And so in doing this, we wanted to first see how the model simulation sort of pre really strong anthropogenic forcing performs. So all of the analysis I'm going to show for the rest of the talk is looking at the 50 ensemble members from the 1870 to 1950 time period, so sort of before a large anthropogenic greenhouse gas signal is observed. And what I'm showing here is standard deviation on the y-axis, this persistence metric, the 6-month autocorrelation on the x-axis. And then I'm just taking decades that have high variance and persistence in the red, decades that have low variance and persistence in the black, and comparing those. So I have these, and it's about 20 decades for the red, 20 decades for the black, and then trying to look at how those differ, why, what the regional characteristics are. So in looking at persistence, I think these plots that others have used previously are to me quite illustrative of what's happening seasonally. And so all this is an autocorrelation. So you can see the month on the y-axis, autocorrelation with those months into future months. And so it's just a metric of the autocorrelation. And you see these interesting patterns where you lose that autocorrelation during summer months.
The problem with using the mouse is the pointer. And you regain that correlation in the winter in some lead months. And so I'm going to stop doing that and just point. Basically decades with high variance and persistence and low variance and persistence have a similar sort of structure to the persistence. It's just you have higher autocorrelations in these decades with higher variance and persistence, sort of by design. So we can look at this for different regions around the Antarctic to see if there's a regional aspect to this expression of persistence and variance. And this is a lot of plots. I'm just going to summarize it by showing you the difference in this autocorrelation metric for decades with high variance and persistence minus decades with low variance and persistence. And what you can see here is that the Weddell Sea on the upper left really stands out as being the dominant region that has increased persistence. You see that this West Pacific sector also has some increased persistence. Interestingly, if you look at the time scale for this, you see that in the Weddell Sea, that increased persistence is through the summer months, whereas in the Pacific, it's actually in the kind of second winter of the anomalies. So there's some interesting differences happening there. But it does look like the Weddell Sea is particularly important. Another aspect of regionality in these things is the possible regional compensation of anomalies. So the leading mode of variability in Antarctic sea ice is shown here. And basically, you get this dipole of anomalies. As you can see, the shaded colors are negative anomalies, the light colors are positive anomalies. So you get this regional compensation of anomalies in the Antarctic. And so a possible hypothesis is that you get high variability in decades where this regional compensation breaks down. So we've looked at that in the context of the CESM2 simulations. And so what we find is indeed this regional compensation does break down in these decades with high variance and persistence. I feel like I should pose for the camera. And so this is just showing the metric I'm using for this is the correlation of anomalies in the Weddell Sea with anomalies outside of the Weddell Sea. So basically the Weddell Sea versus everywhere else. So the correlation shown here, there as a function of month, you can see that in these decades with high variance and persistence, you actually have Weddell Sea anomalies for most of the year positively correlated to other regions of the Antarctic. Whereas in these regions, these decades with low variance and persistence, you have pretty significant negative correlations for the winter between the Weddell Sea and the rest of the Antarctic. So this regional compensation and lack of it in some decades seems to be playing a role here. And we see evidence of that perhaps in the observations as well. So that kind of gives some idea of the regional structure and conditions for these decades with high variance and persistence of sea ice anomalies. And we have looked a little bit at the potential for the atmosphere to be driving some of these differences. So in particular, we've looked at the role of the southern annular mode. So what I'm showing here is the first EOF of sea level pressure, so a metric for the southern annular mode. These are for decades with high variance and persistence. These are decades with low variance and persistence, and these are the differences. And so what you can see is that there are differences in the structure of the SAM between these different decades. And in particular, and there's differences, this is a monthly analysis, I've done this for other months, but the differences are most striking in the ice growth season in April and May. And you can see that in these decades with high variance and persistence, they have a less annular structure in their southern annular mode anomalies. And so those differences in atmospheric circulation can drive differences in sea ice variability, and a lot more needs to be done to actually make those links. But there do seem to be some intriguing differences in the atmospheric variability between these decades. We've also started looking into the potential role for the ocean in driving these differences in variance and persistence. As I mentioned, the Weddell Sea seems to be a particularly important location. So most of this analysis has been looking at transects in the Weddell Sea. So what I'm showing here is a temperature transect in the Weddell Sea. So this is a little blurry, but it's down to 600 meters depth. And then you can see as a function of latitude. So the temperature shown there, the ideal age there, basically those are the sort of mean conditions. And then what's shown on the bottom are the differences between these decades with high variance and persistence minus low variance and persistence. And so you see in these decades with high variance and persistence, you have warmer waters subsurface, older waters subsurface. So it looks like a signature of differences in the circumpolar deep water, and likely a shoaling of the circumpolar deep water. And again, we need more work to try and figure out the mechanism by which that could be driving differences in the variance and persistence of sea ice. But we do see, and again, these plots are really messy, we do see that the subsurface ocean seems to be playing more of a role in the ocean, in the sea ice conditions in these decades with high variance and persistence. And so this is just a correlation map of ocean temperatures, again, along that same transect in the Weddell Sea with Weddell Sea ice area. And you can see that the correlations are considerably higher in these decades with high variance and persistence. So some final thoughts on this. CSM2, I think, is an interesting and potentially useful tool to look at some of these questions on what might be driving variance and persistence changes in the observed sea ice cover. We see indications that the Weddell Sea is particularly important. There's less regional compensation of sea ice anomalies in these decades with high variance. Looks like the structure of the SAM might be playing some role. The ocean structure in the Weddell Sea appears to be playing some role, and a lot more work needs to be done to actually make those links between those atmosphere and ocean drivers and the actual sea ice thermodynamic drivers. So I'd love to talk with people more about this if people have thoughts, and I'm happy if we have time to take questions.
All right, questions from Marika in the room or online? Elio, and they'll turn on the overhead. I think we're good.
Yep. Well, very nice work, very interesting. I didn't understand correctly that when you're showing that plot with the variance and autocorrelation of different decades, and that's essentially in a period without a strong anthropogenic warming. So does that mean that what we are seeing right now might be part of natural variability, because we would see it even if we didn't have anthropogenic warming?
I think that is potentially yes. I mean, I think just internally driven climate variability within this climate model suggests that you can have these decades of changes in variance and persistence, which are not too unlike what we see in the observed state. And so I think that does raise questions on whether this is a regime change or what we've seen in the observations, or potentially just internal variability. Yep. And one of the future things we want to do, of course, is look at how these things change in the warming climate. But we do see pretty sizable differences in variance and persistence just within kind of a not strongly forced climate state.
Are there plans to look at that in the PI control?
So I didn't look at it in the PI control purely because it's easier for me to look at. It's a silly reason. It was easier for me to look at it in the large ensemble simulations. I don't expect it would look very different in the PI control. And will do that before I publish anything on this, just to make sure. But also we wanted to kind of look at, you know, almost like sliding periods of time for some of these things. And so for doing that, it makes sense to start with the large ensemble because we actually have a transient climate. Because we do want to get to that question of how anthropogenic forcing can influence these characteristics as well. Yeah. Yeah, David.
Yeah, great talk as always. I was wondering if you've stratified by whether it's a positive or a negative sea ice anomaly, and whether potentially you see different mechanisms at play causing increased persistence for positive versus negatives.
I haven't done that. So yeah, everything I've done is just looking at the variability. I think that would be interesting to do. And yeah, that's a good idea. And I think, you know, like these ocean drivers, I mean, to me, it feels like this warmth is, you know, more accessible in these decades with high variance and persistence. And maybe that access to that warmth might drive negative anomalies, you know, more so than positive anomalies. So I think that would be an interesting thing to do. Yeah.
You got it.
Marika, thank you for the talk. Maybe I missed this part of it. Can you say something about how do you calculate or estimate the persistence and the variance?
Yeah, so the persistence, I'm just estimating by a 6-month autocorrelation. So it's a very simple metric. You know, so I'm looking at the monthly anomalies, and then a 6-month autocorrelation is my metric for persistence. My metric for variance is just the standard deviation of anomalies. So very simple metric.
6 months?
So these are all for decadal periods. So I have, so what I'm doing is I'm taking decades. So each point here is a decade. And that's the standard deviation for that decade, the 6-month autocorrelation for that decade in terms of the monthly anomalies. And then I'm taking the, you know, 20 lowest, I think it's 5%, 20 lowest decades, 20 highest decades, and then I'm lumping all those together. So I have 20 decade, you know, 20 times 10 years, something like that, that I'm doing for each of these composite analyses.
What's the reason to only the 6 months on the correlation? How about 1 month, 2 months, and then do some kind of average?
Yeah, I mean,
What's the consideration in it?
for the 6-month, it's partly because it's been used in some previous work using a 6-month autocorrelation as a metric for persistence in some of this Antarctic sea ice stuff. So I was doing something similar to what others have done. Yeah.
Well, last question.
Yeah, I was just kind of curious as to maybe similar to Dave's question, but with looking at kind of like anomalies in the MAPS budget, help you to try to kind of like isolate kind of drivers coming from the atmosphere or ocean.
Yeah. I mean, that's what I want to do next exactly is, you know, and so things like the EOF pattern, right? I mean, I think you could look at the EOF, the time series is, associated with the SAM and look at how that is related to the mass budgets in different regions and use that to gain some insight on what to drive, on how that can be linked to the sea ice variability. So that's exactly what I want to do next is look at things like the mass budget terms for both the atmospheric drivers and the ocean drivers to try and get some mechanistic understanding of how these differences in these decades are driving differences in sea ice variability. So yeah, my thoughts exactly too. All right, thanks.
Thank you, Marika. All right, so the next group of today we have scheduled as a discussion. So we'll all be in there. Hansi, my co-chair, is going to present. I think there's something that's called like discussion slides that you guys have found.
Discussion slides, yes.
Oh, and I think Hansi can share them directly if you put her up there. You good to do that, Hansi?
Yep. Can you hear me?
Yep, we can hear you.
Awesome.
So kind of the theme of this discussion we thought was going to be science and society. So we've had a couple talks about that. And are you sharing the slides, Hansi? Because if so, we don't see them.
Yeah, give me 1 second. I'm trying to find the right window.
Okay. So Hansi's just going to share some thoughts, and then it's kind of open discussion about maybe directions we want to take the Polar Climate Working Group in terms of making our science relevant for society in different ways, or any other thoughts like that. So that's kind of what we envision, but it's free flow. We don't have a super specific agenda. All right, it's up there. It's if you click slideshow. Perfect. Okay, that looks great, Hansi. You're muted.
Why did it mute me? I didn't do that. Okay. Thank you for being here, and sort of excited to hopefully get a little bit of discussion going about our science that we do and broader society. So as you know, y'all, we are currently living in some difficult times for science. So as you know, there's been layoffs at major scientific agencies like NSF, NOAA, and DOE. At NSF, there was even a question about whether grant payments would resume, which they have, but this is on court order. We don't know if there will be issues with this in the future. Review panels that were canceled are being resumed, but there is a lot of sort of internal goings on at NSF, from what I can tell, in terms of complying with executive orders. And then NOAA, our, really near and dear scientific organization, because it's oceanic and atmospheric, has just had a huge number of amount of its workforce that has been taken away, in addition to a bunch of people that have voluntarily retired or voluntarily allowed themselves to be let go because they will be paid until September. And we don't really know where these cuts have happened, but there is some sense that perhaps some of these cuts have been to critical staff, so including National Weather Service meteorologists. And for example, like these are the folks that issue weather alerts. So pretty high stakes cuts, I think. And then, of course, the future plans for NOAA are uncertain because it is, quote unquote, part of the climate change alarm industry that I've heard from what the current administration has been saying. And then in DOE too, there's been a bunch of cuts, and we don't know how deep those will go in the future. So one thing, though, that to say is that despite all of this turmoil, global trust in science and scientists is still really high. So most people, and this is from a study from January 2025 in Nature Human Behavior, most people still view us scientists as qualified and honest and concerned about societal well-being. So that is great, right? The public, though, seems to have certain requests from us. So one request is more engagement and communication. Another one is more involvement in policy making. They want to see more of us scientists actually involved in, what makes government and society tick. And then finally, some people, there's a contingent of people that believes that scientists don't necessarily pay attention to the concerns of others. So that is maybe an area where we might seek to make some improvement. So for this discussion, there's kind of a few areas that I really sort of want us to think about. And I think, we don't have that much time. So whatever people find interesting, I think it would be great to talk about. So first of all, Laura touched on this regarding the timeliness of the information that we provide. So is it timely and is it relevant? So one of these areas that's actually quite interesting is these very recent LA wildfires. NOAA, as well as ECMWF, as well as lots of other weather forecasting type agencies. Generally, like NOAA, for example, only gave an alert the day before these fires, even though if you look at their forecasts, you can see that there probably could have been warnings and alerts that went out a week early. So, I mean, I think like, yeah, this is always the issue, right? Like, does the information come out in a timely way? And I think some of this does have to do with maybe not enough personnel, but maybe it also has to do with, do we play it a little too safe sometimes? I don't know, but this is just a question for us to think about. And then some other questions. Are we providing the information that the public cares about? And can the things that the public care about be derived from those? In other words, like, you know, is there enough information for people to get the last mile of information out? In other words, you know, the difference between essentially like scientific information and then real world information that people can use to make impactful decisions for their communities or for their businesses. And so, you know, how are we bridging that gap? And then, as Laura has also mentioned, do we listen to the communities that are interested parties to our science? Do we even have time to do this? Probably the answer to that is no, in terms of having the time. But, you know, I don't know. I mean, I think one thing I would love to see is that more and more people see the value of science in the public. And I think some of that value will come from some of these communication type activities. And then finally, as Earth system scientists, I mean, you know, we study climate and climate change and things that deeply affect people's lives. And so the question for us in particular is, what are our responsibilities as stewards of science and discovery, particularly on a planet that to some extent is in a major transition. And so, you know, to just kind of summarize, right? I mean, you know, let's maybe try not to be like this guy who does not know how to communicate their science. And yeah, how can we perhaps be better at telling the compelling scientific stories so that our interactions with society are perhaps existent and positive. So yeah, would love to hear people's thoughts. And I think this is like a really important time to discuss all of these things, just given the latest news, et cetera.
All right. Thank you, Hansi, for starting off that. I think the roof mics are on. Will you guys put the tiles of all the people? So anyone who's online, you can turn on your video, and we want this to be more like a conversation. So you don't have to turn your video on, but if you want to, we would love that. And then it's kind of just discussing ways that we maybe can make this sort of polar science relevant for communities. Maybe some of that is like how to work with foundations. Laura and I were talking with Daniel some about like what sort of geoengineering type research could be interesting and maybe more relevant for communities. And that kind of went off of the talk that Cecilia Bitz gave last Friday about geoengineering and where that might be useful for sea ice. So things like that are the types of things we want to talk about, but I'm not anticipating that I will continue to stand up here the whole time, or that I will not be talking the whole time. And you can come closer to the three in the back. Yeah, Kevin.
No, start things off, I guess. I really appreciated your presentation about the part of having an intermediary between the scientific community and kind of mass public communication. I think that we don't have enough time and skills to do that directly ourselves right now, and we're going to have less time in the future. I think those partnerships could be a way to do it, or at least very important. And as you've been pointing out, the last election basically proved that we need to have a very impactful emotional message get communicated to the public, because that's what really sways the largest fraction of the public.
Yeah, I think that's accurate. One thing I've also found doing some of that work is that most of the policy space, at least that I've interacted with, their tool of choice is GIS, not NetCDF stuff, and having a simple way to be able to use our climate models and put it into GIS world having something like that would be really valuable. And I don't know that the Polar Climate Working Group has to be the only one that does it, but if we see value in that sort of stuff too, especially for telling stories, I think that's something that could be beneficial to all of CESM, honestly. Marika?
Just following up on that, how do we foster or how do we even find those kind of bridging entities, right? I mean, I agree that in the project Alice talked about, that seems like a really valuable way to tell stories that can be impactful and involve policymakers and things like that. But I'm not even quite sure how to find those groups and how to approach them. And so I don't know if other people in the room have ideas about that, but or if there's something the Polar Climate Working Group could do to find those bridging organizations and how to work with them or something, but. Do you want me to take notes so you can run this?
Okay. You're eating your popcorn.
I am.
As long as you don't start throwing at me.
So much fun.
Yeah, I tend to think that to some extent, some of this is that possibly, I mean, so in other types of science, so I don't know, like, I mean, the big one is like biotech and pharmaceuticals. You tend to have a lot of scientists that are actually like actively working in the real world, perhaps not as scientists, but in these kind of bridging roles. And I feel like maybe in our disciplines, like we tend not to do that as much. And so I think that makes this whole bridging thing even harder, because I do think that you sort of need the scientists to bridge, because as any of us know who have talked to journalists, for example, like it's not easy, right? And so I think it really suggests that like science communication by scientists is in itself like a really important specialty. And maybe it's not even just communication, but it's like communication and policy and different ways of being able to communicate with the public and understand their needs. So then it's easier for the actual scientific community to be able to continue to do its work and also at the same time be able to provide sort of whatever is impactful. Because I do want to say that, I mean, I think like the investment in the basic science is so important, but I think that without that sort of go-between, I think our community ends up being very, very isolated.
Alex?
Yeah, I mean, I think one way to, in the future, maybe try and do this more is kind of with new proposals as a broader impact, since some of the things that we've been doing might not be as popular in the next couple of years. But we still need the broader impacts and kind of to see if there are places out there that we could kind of collaborate with strategically to kind of, and maybe also with several people so that they kind of become experts in communicating this kind of polar science, and to have like a public outreach product strategy, that kind of thing. And I don't know who that would be. I don't have any contacts, but maybe someone has done something cool in the past or seen something, maybe not even for polar, but for other climate science or something that would be worth kind of exploring and then sharing so that we don't all have to reinvent the wheel every time we write a proposal.
I mean, that makes me wonder, and I know CU best, but I don't think this is limited to CU, but like CU has PASECO, which is this polar early career scientist. I don't know. I don't remember what the acronym all stands for. Sorry. But, you know, like UW might also have something that's like an outreach group, and maybe it's, you know, partnering with those groups more, so that we're not reinventing the wheel and we're going through channels, something like that. The other thing I wanted to point out that Kevin brought up and that Marika brought up too, is some of these bridging organizations, at least for the Theantarctic project that I've been working on, it seems to me that the bridging organizations are very much in this philanthropic world. So like one of the CU Boulder collaborator on it works a lot with the Pew Charitable Trusts, and she's able to get grants through them. And only one has a couple like private donors who sponsor most of the work, a lot of the work they do, at least for the Antarctic Project. They have some other parts of the world. And I do feel like for some of these bridging organizations, being able to tap into this private money aspect of things will be even more important in the future, just depending on what happens with where government money goes, if we're able to do that better. And we know this isn't just limited to NCAR, but we know that we have challenges with that in NCAR. And so I think trying to figure out ways to work within that space, maybe it's partnering with these groups so that they don't have to pay our overhead, but they're a partner on a project or something like that. Maybe, you know, maybe they're on the proposal to NSF and they're not asking for money, but we're able to leverage some of those resources or bridging, something like that. David? No? You just,
Sure, yeah, no, I can,
couldn't tell if that was a hand raise or like a hair flick and say something.
it wasn't, I mean, I was thinking though, so I couldn't say what I was thinking. I mean, having, you know, really minimal experience in this world, I wonder if we should also think about different communication strategies for problems on different timescales. Because I think that's one thing that, you know, if it's a problem that's going to hit someone in the next year, the way you communicate it and who you communicate it with could be very different than if it's a problem that's going to hit them in the next century. And we should, and I think right now it feels to me like there is a desire from at every level to get to the most granular level of stakeholder and be able to demonstrate engagement with them specifically. And I think that's really valuable on the short time scale problems, but that tends to potentially just add more confusion on some of the longer time scale problems, because they, you know, they're not worried about the next century. They're worried about getting through the next couple of years.
Yeah, just following on that. I mean, I think, you know, there is a group in M-Cubed who thinks a lot about communication of weather risk, right? And there might be some value in teaming up with people like that who are thinking, who have expertise in communication strategies to think about these longer term risks, some of which, you know, is the stuff we're researching. But I think, you know, that could be kind of interesting, and pulling them into these projects might be a good way to do it. You know, it's kind of a broader impact, thinking about the communication strategies, because we're not trained in those kind of things. But there are people that have expertise in that. So I think that could be a really, you know, I'm thinking of people like Julie DeMuth or others who, you know, Rebecca Morse, they think about communication strategies for, you know, weather alerts and things like that. And we could ask them to help us with how to communicate polar climate risk.
Yeah, I think that's like such a good idea, because you're totally right that there is kind of group of people that already has experience with a lot of this communication because they interface with the public a lot. And yeah, in terms of these different timescales too, if you start telling people about, at least like from, you know, what I found sort of talking to people in a lot of different sectors, if you start talking about the 100-year problem, it's very easy to lose people. But I think people are much more interested in the problems that they see emerging here and now. And I think like we have plenty in that area to talk about. I don't think there's any shortage of, you know, impending climate impacts right now. And so I think that sort of immediacy is helpful.
Is there anyone else online who has any thoughts? I want to make sure that, you know, you're welcome to either raise a hand or unmute and speak as well. All right, I saw Keith's hand up a minute ago and then Julie.
Similar to what Mariko was saying, there's a communications office here at UCAR that has experience on communicating the messages of scientific content out to a broader community. That's one avenue. Another is asking people that do this, what are their answers to these questions? In another is like there are certainly prominent science communicators, whether it's people at the level of like Catherine Hayhoe or Daniel Swain. You always see his name if there's a big storm in the Southern California, or Gavin Schmidt, people that are prominent science communicators. I'd be curious to see what their answers to these questions are.
Yeah, just speaking from, so Elio and I are part of an Antarctic Center in Australia. And one thing we found is this saying that what happens in Antarctica doesn't stay in Antarctica has been really effective. And I think someone had that on the Friday talks. And so, and I know in other working groups, they're linking, Antarctic, Southern Ocean cooling to tropical Pacific cooling. And if you could try and share those stories that are really going to affect people in the US, that's definitely something I think we've found in Australia where we've seen, links between the polar vortex and Australian weather has been really good at communicating to the public. And the other thing we've done a lot in Australia is hire knowledge brokers, saying you can do that in this current climate, but we've submitted a lot to parliamentary inquiries. I don't know if that's another thing that people at NCAR are doing, and it's really raised the profile of our centre with politicians to know that we're and government agencies that they can come to us if they have questions about the science.
You said they were called knowledge
Brokers, and so they're sitting at our universities, and they're kind of translating our science into something that we can then take out.
I think it's also, we're talking a lot about communicating science, and I think a lot of people do communicate science, and there's press releases on our papers and things like that. So I think thinking of these other ways to communicate science, like I think Laura and I were talking about TED Talks the other day, it would be interesting to think about just other avenues, like besides the standard things we do, like the press release. I know there's some of the work that Laura mentioned or showed today. Like there's a film being produced right now on changes in walrus and hunting access to walrus. And that, could be an impactful film. I don't really know that world, but so I think it's also, as a group, it would be interesting for us to kind of think about full stories that we have and then communicating them in a very different venue than we're used to, like a TED Talk. And there's some great scientific TED Talks from some of the people we have mentioned here, like Gavin has a great TED Talk on climate modeling and things like that. But anyway, maybe thinking of those venues would be good too.
Yeah, and kind of along those notes, so of course there's people who like communications officers and stuff who are experienced in talking to the public, but another group that has a lot of experience putting things in terms that get across to people are like artists and writers. And that's something that at CSU, we've worked with artists before. We've worked with both professionals and students and found that to be really fruitful, both because the artists can help us interpret the science, and then the artists are also learning about what we do. And those are fields that don't always talk to each other very well. And particularly if you're working with students, that's a way to do this without to put it bluntly, without needing a ton of money. And they're still getting a lot of experience and opportunities that they wouldn't get otherwise.
Yeah, just following up on that, at some point, the Dairy Center, just because I have a mutual friend with the director of the Dairy Center, so she approached me and she was like, oh, it'd be really cool to do some exhibit on climate change.
And I was like, yeah, it would be really cool. And then that's where the conversation ended. And this was like 3 or 4 years ago. But we could, I mean, I think it would be fun to figure out how to pursue those kinds of things. And maybe approaching students at CSU and CU and getting some art students involved with the work we're doing. That's a great idea. Maybe some film students too, right?
I was going to say for the Antarctic project, one of the people I'm working with who's a photographer, videographer, John Muller, has a bunch of, not canvases exactly, but I mean, talking to some of these people and seeing if they have anything that they could already display, or, you know, maybe a mix of those sorts of things. Like we don't have to, everything doesn't have to be new, but being able to show some of the work that already exists might be good.
Yeah, I think I would love to see more, I think, philanthropic money coming in for these kinds of science to public communication type ventures. I think that, like, yeah, I mean, I'm not exactly sure like what we can expect in the longer term in terms of NSF and NOAA, but I think we can probably expect that their budgets aren't going to go up. And costs are constantly rising. And so, you know, the question is like, where is the money to be able to do some of this? And I do think yeah, we can probably be creative in terms of how we think about where this money could be sourced.
I guess this is a little bit of a separate question. This is a little bit more directed at you, Elizabeth. Sorry, I'm staring right at you, putting you on the spot. Are other centers, like is E3SM, are they working with communities to try to use these higher resolution simulations to like answer questions, you know, the near term questions like a community wants, or like what sort of science for, you know, different parts of society are you guys doing? So I think that's one of our challenges with the low resolution model is sometimes I feel like communities are like, but I care about this lagoon.
Yeah. For E3SM, its focus has always been on DOE as its stakeholder. But DOE is part of the larger intelligence community. And so the applications that I see, at least at Los Alamos, tend to be toward national security kinds of questions rather than environmental type things.
I will say that at PNNL, which is of course a different DOE lab, and it's not a weapons lab like Los Alamos, they are doing a lot of work with energy folks. So there's work with like electric grid providers and yeah, lots of, it looks like a fair amount of like collaboration within the state of Washington and other Pacific Northwest states. So there is some good work going on over there.
I guess I wonder too, this wasn't a presentation today, so I will just inform you all that there is a project here at NCAR called Crocodile, which I have no idea what that acronym stands for. But the purpose of it is to make like a regional ocean ice grid with MOM6, which is the new ocean model that we'll be using for CESM. And one of the big open questions is how do we do regional sea ice boundaries? But I feel like I could see a lot of applications for something like that, like to span this space, like Hansi was talking about, where we still need CESM type models that run to the end till 2100 and provide some idea of the internal variability. But if you compare that with these like very regionalized versions of a model and look at how you would run it would depend, I think, on what the questions are that whatever that community is interested in. I guess I see a place for expansion with that within Polar Climate Working Group is to try to pair more with them and figure out how to use these regional models for answering questions that different communities might have. And it might be, you know, it might be Antarctic, like the Australians care about their, or I mean, maybe it's less likely will be funded cross-trailer. So the US cares about, the sea around McMurdo Station, and so we're doing something there, but it might also be, a community in Alaska or, somewhere around Greenland when we're trying to figure out where to go in. Anyway, I can probably not that we're doing that. The intelligence community is doing that. But anyway, I guess I see that there could be very clearly a link between these regional models that can get to be higher resolution paired with the knowledge that we bring about internal climate variability and longer change and stuff like that could be really valuable. Laura?
Yeah, I was just, I'm a firm believer in trying to support and build community through a lot of different bridge makers and a lot of different perspectives. And I can't help but wonder if there would be some possibility, I don't know if there'd be a private nonprofit that would fund this, or money might be another question, but opening up some like student internships here that were targeted specifically at journalism majors or political science majors or history majors, because these people often, they're also telling stories with a different perspective perhaps, but that reach a completely different audience. And if there was some way of doing like, I don't know, getting an endowment to do a summer internship every summer and have it broad enough that you could get a lot of different applicants, and have some sort of, at the end, they'd have to produce it or publish it in a certain, I don't know, somebody else, to look at people outside of our fields. And I think of this experience that Alice and I had this past summer mentoring a SOAR student who was not doing atmospheric research in a traditional sense, but rather a history major who is interested in looking at how Arctic traditions are changing with changing climate. And I didn't actually witness it, but his stories of when he took his work that he did with us this summer to AMS, is he had a fantastic time at AMS. He had a lot of people who were highly engaged, highly interested in his presentation and his talk. And maybe there's also some other avenues that we could explore to engage people from other disciplines.
Annalise?
Yeah, maybe more of a point of view of a PhD student. It's like a PhD is a short, limited amount of time, and usually they want you to like talk about a specific topic and get like having 3 papers by the end. But could we do like hybrid PhD where you have your focus on the topic and also doing outreach? Because I know that a lot of PhD have an interest in doing outreach, doing like a website, or they are artists and they want to translate that, but they don't have the time to do that in their like 4 years PhD. So yeah, maybe like switch the focus from papers, scientific papers, to something more artistic and yeah, available to the public.
Yeah, to build on that, not only for PhD, but for at every level of the scientific career, I don't know that we are valuing that kind of outreach that we are talking about here. Like if you're almost a professor and you want to get tenure, and you have to decide whether you want to spend your time getting yet another paper that is going to get you closer to that, or you're going to spend time on an outreach project that maybe you might be able to spin that into a paper, but you won't get like a Nature cover for that, or a paper into a high impact, quote unquote, high impact journal. Then when you go for promotion, then are people evaluating that correctly, or is that what you value?
Yeah.
I think relatedly, yeah, we have a fundamental challenge of things that we value but are not valued by funding mechanisms and by career advancement trajectories. It seems like a big challenge that we've identified a lot of things that could really use improvement, and yet there is not funding to support those things. And yeah, not as Elio and Lee said as well, not the structure within tenure track positions or PhD time lengths to accomplish these necessary steps. I don't have any answers. That certainly seems a challenge, though.
Sorry, I've got a dry throat here.
Yeah, I mean, I do think that this is like, it's not valued at all. And I mean, I think a few thoughts come to mind. I mean, like, I think the scientific sort of like discovery is so important for itself. You know, there's no question about how important that is, but I think this is why we need to figure out other mechanisms in terms of making sure that there are scientists that are still doing a lot of this. And I mean, I will say, like, being in the private sector now, that there are companies that literally do possibly your science, and there is not like a single like actual PhD scientist at that company. And so, I mean, it's like, if we don't engage with this stuff, then like other people are just gonna take whatever information is out there and run with it without knowing what they're doing. Just a couple of examples. There is a sea ice prediction company, for example, called Polarctic. So I think they're doing sea ice prediction for marine shipping and insurance purposes. And then there is also a company actually doing geoengineering called Making Sunsets out there. And they are literally setting up balloons into the stratosphere and getting paid for that through what they call cooling credits. Those are just a couple of examples. So it's the Wild West out there without y'all. And I know probably this is one of those things where, you know, I'm just preaching to the choir because everyone here understands, but yeah, it's pretty wild out there.
Any kind of getting towards the end of the discussion, any other thoughts people want to raise? Yeah.
Well, so how do we bring in money to be able to do this? Or how do we, you know, maybe we start our own company. Hansi already has, so you know.
I think that shouldn't be considered a joke, honestly, for this kind of stuff. I mean, if there is a future in which and no longer federal entities are competing to provide this kind of information, I think particularly, you know, if you're making a prediction a week from now and you're making those predictions repeatedly, someone can figure out whether or not you're feeding them garbage, essentially. But for the kinds of information that's needed for a lot of climate questions, which are decades from now, you won't get a chance to get that feedback. And so having a source of that information where you trust the process that it comes from could actually be quite competitive in this world. I mean, historically, that's been the role of governments, but.
Yeah. Yeah, Courtney. One other thing I think we haven't touched on so much, but the kind of stakeholder focused and driven science that like Laura and others in this room work on is, I think, incredibly important and certainly has consistently been undervalued by our existing funding mechanisms. I think that work takes a lot of time to build relationships and trust and, you know, knowledge on both sides. And a beautiful new world that I think we'd all love to imagine. I feel like that would be another place that I would love to see increased focus. And it all comes with many challenges as well, but yeah.
I guess maybe something, at least the NCAR people could bring up is, like, I know that there's this Prince Albert and Monaco Foundation or other things like that. Like, is there anything that, are there any prohibitions about us approaching or like trying to get nominated to go to things like this. Or like, this is just another example, but like my husband does drone stuff and his research group got to go to this Mars conference that Jeff Bezos puts on. Just no comments about Jeff Bezos at the moment, but things like that. Like, I just don't know that NCAR, like, are we allowed to nominate to those types of things, or is NCAR, UCAR as a whole, like, trying to get into that space? And like, if we're talking about not just philanthropic, but like those kinds of private money, I don't know that there's a whole lot that I know about on the NCAR side being done, and maybe that means we should do it with our copious spare time. But yeah, I don't know. Yeah.
I did just want to say that there's going to be a panel discussion hosted by Schmidt Sciences in May. I need to double check like who that's open to, but I've been asked to speak on like an early career panel there. I think that might be a good opportunity to raise some of these points about, what do we as a science community need from these like philanthropic funders. And if it's open, then that'd be great if like people could join and ask these kinds of questions. I can get back to folks on that.
Yeah, I think Schmidt Sciences is great when, I've talked to them before. I think they're mostly doing work purely on the science side. I think that there's a lot of foundations out there though, like say the Gates Foundation, the Packard Foundation, many that are out there that are doing work at the intersection of like science and society. So I do think that there is a big philanthropic world out there. The downside of the philanthropic world is that it's like, it's not very, like, it's not like NSF or, various agencies where it's very clear what what hoops you have to jump through to get funding. Like a lot of these, foundations are sort of about who you know. It's a very opaque process from what I've heard about, but honestly, I mean, it shouldn't be. And I mean, there should be like some weight to the NCAR name. And so I feel like, yeah, I know y'all don't have much time, but I feel like there's potentially a big kind of well that can be tapped there. Though on the flip side of this, though, I do think these philanthropic funders are definitely under a lot of pressure right now because of the dismantling of U.S. aid and other agencies that previously were doing this work. So that's kind of the downside as well.
I mean, there is private foundation money coming to NCAR. It's just at a fairly limited level, but there's multiple different entities that, people have grants through Schmidt or Grantham or Quadrature or, so I think it's maybe thinking about a more deliberate strategy for how to do this or, whether there's there's foundation money that's funding climate science, but what other things are out there. But I also think just kind of a more coordinated and systematic approach would be good. Right now it's very piecemeal, and then the overhead issue becomes a big problem too. So, but that's a NCAR management question, some of those things like the overhead issues.
The overhead is too high at NCAR, is that the issue?
Yeah, most private foundations don't want to pay our overhead rates. I mean, they'll pay, very low overhead. And at universities which have endowments and things like that, they have a ability to make those up in certain ways. For us, it's traditionally been a challenge for how to navigate that, the low overhead rates that they're willing to pay. It's limited our ability to be involved in some of these things like from Schmidt.
All right. Well, I think most of this was not particularly specific to the Polar Climate Working Group, but sounds like there's interest in trying to figure out ways to fund and who might be good partners for these bridging organizations. I think there's been a lot of talk over time about trying to put value not just on papers, but on other types of work. And I mean, hopefully that's changing in many places. I think it's maybe slow. Are there any other final concluding thoughts people have here? That was like the phantom sneezes. All right, well, in that case, I would say it's 4:24. I can see that the rain or snow or sleet or whatever that is has come in. We will adjourn for today. We'll be back tomorrow. We start at 8:30. Well, we'll start at 8:25 and the first talk will start at 8:30. So I hope we will see most of you there and have a good evening. Hopefully there's not piles of snow around. And we'll use the same Google link. Yeah. Tomorrow.
Thank you all.